Dear colleagues, we are glad to start our second day of our Nano conference. And now will be section Plasmonic and Surface Enhanced Spectroscopy, together with section Nano-objective microscopy. The first topic will be done by Anastasia Tomchuk from Taras Shevchenko National University of Kyiv. Please, Anastasia, you will be the first today.
Він не світиться. Ага, он світиться. Все є. Okay, good morning. I'm Anastasia Tomchuk. I'm a PhD student at Physics faculty at Taras Shevchenko National University of Kyiv. And today I want to tell you about Argentum laser-induced periodic surface structure with aurum nanorods as plasmonic nanocavity metasurface for strong enhancement of adenosine nucleotide label-free photoluminescence imaging. So, fluorescence spectroscopy is one of the most sensitive spectroscopic techniques for use studying physical processes in living systems, and surface-enhanced fluorescence technique has been applied to the label-free detection of biomolecules, including deoxyribonucleic acid bases. So, but high quantum yield of intrinsic fluorescence and phosphorescence of main nucleotides is achieved only at low temperatures. And at room temperature, the studied quantum yield of deoxyadenosine monophosphate is known to be 7 times 10 to the minus 5 power. It's very low intensity. But in our study, we achieve strong enhancement of photoluminescence, DMP molecule by a plasmonic nanocavity composed of silver lip structure and gold nanorods. Here is a scheme of studied samples, and here is DMP molecules deposited on different substrates on smooth argentum surface and laser-induced periodic surface structures on argentum, and the same structures combined with aurum nanorods and aurum nanoparticles. It's a well-known fact that nanoscale metastructures could increase the excitation efficiency due to the excitation surface plasmon resonance. And combination nanoparticle with metal film, we can build nanoparticles on mirror structures, and at these structures arise collective plasmonic mode, so-called gap mode. And it's arise due to the hybridization of plasmonic mode of metal nanoparticle and propagating surface plasmon polyurethane. At this resonator, electromagnetic field is squeezed into very thin gap between nanoparticles and film, and so we achieve strong enhancement and generation hotspots maybe. To analyze our fabricated nanoparticles and nanorods, we make transmission electronic microscopy, and we can say that our nanorods have perfect rod shape and nanoparticles have perfect sphere shape. And also we made finite difference time domain simulation to see electric field for nanorods. We study our lip structure with scanning electronic microscopy, and we can see it here. And in last step to produce our metasurfaces is drop coating of our nanorods colloid on the substrates, and the same morphology we can see very little white dots here. That's aurum nanorods inside the hollows. we take absorption spectra of water colloids of bare aurum nanorods and combination with DMP molecule. So from here we can say that spectrum of spherical nanoparticles have only one peak, and spectrum of nanorods have two peaks, which connected with transversal and longitudinal modes. And that one at 260 nanometers, it's intrinsic absorption of DMP molecule. This is a reflection spectra of studied metasurfaces, and here is a big, deep depth here, and the bigger one is connected with best for surfaces for our destination. That's argentum laser-induced periodic surface structure, and aurum nanorods, because here is best interaction with light. Here is photoluminescence spectra of our substrate, and we can see here that DMP molecules based on smooth quartz surface has very low intensity photoluminescence, and we can detect only fluorescence. We even can't see phosphorescence here. Yes, F is for fluorescence, and this 2-based peak is for phosphorescence. When we connect DMP molecule with argentum substrate, we have with smooth and with lips surface, we can increase fluorescence intensity and very good increase at phosphorescence intensity. We can say yes, fluorescence intensity is higher for molecules deposited in laser-induced periodic surface structure, and fluorescence intensities even don't differ slightly for these both surfaces. It's because a stronger plasmonic enhancement of phosphorescence than fluorescence, because of close allocation that wavelengths phosphorescence with spectrum of surface plasmon polaritor spectral region. And aurum nanorods at this surface, when we add here aurum nanorods, here stimulates processes of plasmonic near-field coupling. Aurum nanorods localize surface plasmon modes with propagating surface plasmon polariton modes at argentum surfaces, and excitation of collective gap mode. So also we made photoluminescence microscopy at visible region, and here we can see that we can see DMP molecules based on our metasurfaces at blue region, but when DMP molecules are on the quartz, we even can detect these. To confirm our idea about excitation luminescence bands, we make excitation spectra at wavelengths of luminescence and phosphorescence, and here we can see only one peak, this at 260 nanometers. So we can see that we can say that this is confirmed emission spectra, that all emission spectra belong to photoluminescence of DMP molecules. To make some quantitative results, we calculate enhancement factor and obtain enhancement factor for total photoluminescence change from 300 to 1,200, and for fluorescence it's a little bit smaller, but the biggest enhancement factor is for combination nanostructure with argentum lips and aurum nanorods. so it's very good quantitative, they say, and so from that we can say that from presented data we can say that plasmonic gap mode has crucial role for enhancement of fluorescence. And for end, I want to say that we demonstrate the combination of lip structure and non-spherical nanoparticles as plasmonic cavity metasurfaces, and we have very good high sensitive fluorescence, and we can use this for sensitive detection and imaging biomolecules at room temperatures. It's important. So here, if we use such metasurfaces, we don't need to use any auxiliary dye labels for imaging of nucleotide photoluminescence, and these findings can be very useful for development of plasmonic metasurfaces, having the possibility to control the enhancement of separated photoluminescence components by changing form and material of metal substrate and nanoparticles. Thank you. Thanks for attention.
Thank you for your interesting talk. Any questions?
Can you please say me, typically, when you place your some species, fluorescent species, on directly on some plasmonic structures, you have no photoluminescence due to very efficient energy transfer between your species and plasmonic structures. So typically, to enhance photoluminescence, fluorescence, you need to make some distance between your species, and this is a very significant difference between, for example, SERS and photoluminescence enhancement. And as I understand, you place your DNA molecules on your surface directly. So and also you have, for example, for our nanorods, very significant difference between plasmonic band and your luminescence and of your DNA. So what's the mechanism of such strong enhancement in your case?
We have some distance between nanoparticles and DMP molecules or nanoparticles and lip structure, because nanoparticle was a colloid liquid, and here is some molecules that cover nanoparticles, and these molecules have some few nanometers thick, and some nanomolecules don't lay on the lip structure by itself. It's some distance between it. Is this the answer?
Okay.
So
Questions? Any questions? More? Okay. Thank you so much for your interesting talk. And our next speaker will be István Kasarnovics from Hungary. István, can you hear us? Hello? István, can you hear us? Hello?
Yeah, I'm here.
Hello, we were waiting for your talk. Please start.
Okay, good. Доброго ранку. Good morning, everybody. I'm from Debrecen, from sunny and very cold Debrecen. I hope you see my presentation. So I would like to talk in a very few 15 minutes about investigation of SERS, surface enhanced Raman scattering, with different gold nano-islands, with different analytes. So I'm from Debrecen, Hungary. I'm working in the Faculty of Science and Technology in the Institute of Physics, Department of Experimental Physics. But basically I was born in Ukraine, in Transcarpathia, in Uzhgorod, so that's why I was very happy to join this conference. Unfortunately, I couldn't join the conference offline, but I'm very happy that I could join it online. So I will give you some inputs. However, I think this community, you already know a lot of things about the surface enhanced Raman scattering, about localized surface plasma resonance, and after that I will give you some inputs about our results, how we created, investigated the structures, what kind of interesting connections we found out between their geometrical parameters and the enhancement, and how we examined all these things. So as you know, the surface plasma resonance could be very nicely generated on the surface. We could use just a moment. We could use, if we have a single layer of gold or silver or any kind of metal, we could create surface plasmons using a prism or using grating. However, if we are creating nanoparticles, then we don't need any kind of complex structures. We just have nanoparticles, and depending on the shape and size, the material, we just irradiate and create nanostructures and plasma. So let's see how they could be used in optical sensing. So they could be used, first of all, with well-known structure for a surface plasma resonance or surface plasma resonance imaging. When we have a prism, we have a thin gold layer, and we are irradiating the polarized light, and we are checking the reflection. And if any kind of structure will be attached to the surface of gold films, then we will have a change in angle or change in intensity, and in this way, very nicely, any kind of refractive index change or any kind of attachment of biomolecules could be thin. For LSPR type, so using metallic nanostructures, for example, we have some kind of legend, we are putting some kind of analyte on it. The analyte is changing the refractive index, and as you could see, we have a very nice plasmonic peak, and if the refractive index will be changed, the plasmonic peak will be shifted to mostly to the higher wavelength region. Sometimes in the experiments we see that it's shifting to the lower. It has some artifacts effects, of course. So basically, when we are using LSPR for sensing, we have a resonance peak for the pure nanoparticle system. So we are using the light source, irradiating a surface, and we're checking with light detectors such nice optical things. And if you are putting some analyte on these structures, then this peak will be shifted. And of course, the sensitivity of the structure depends on the peak shift and the refractive index shift. So on these two things, we could play, and people are trying to increase this wavelength shift to have a higher sensitivity, because the refractive index shift couldn't be changed at all if you are using the same analyte, of course. The SERS, if you are, I think this community already known what is it, so I don't want to lose a lot of time, but if you have a matter, then the light matter interaction, we could have a transmission, we could have a reflection, we could have a scattering, and one of the main important for us scattering is the Raman scattering. During the Raman scattering, we are losing a lot of intensity, but we get a very nice information about the structure of molecules. For example, this is our structure, so we have glass and we have gold nano-islands on this glass. For example, in some cases we put benzophenone, we are irradiated with lasers, and the signal will be reflected back, and the signal could be checked with microscope, spectroscopy, and it could be said how these nano-islands play a role in the intensity. However, before I'm starting to show the results, some very small input to the Raman scattering. It's a very nice technique. I started to work with Raman spectroscopy approximately 6-7 years ago, and we are very happy because 2 years ago we got our own equipment. It's a non-destructive, effective analytical tool for material characterization because it's using a monochromatic, very high intensity laser irradiation. It's an inelastic light scattering taking place, and that's why we could check the bonding structure can be determined for this. Only one very important disadvantage, that is very weak signal we get, so that's why we need something that could enhance the intensity of the signals. The breakthrough was when people discovered approximately 10 years ago, a little bit more, the SERS effect application of metal surfaces. So if you have a metal surfaces here, silver nanoparticles, and we are putting some kind of molecules on it, we could nicely see how much it's increasing, enhancing the signal of the Raman spectroscopy. So it's really, really nice tool to get it. What kind of materials could be used? People using different materials, I agree, different shape, different size. So you could see that basically, if we would like to play in the visible region, people using the copper, silver, and gold. Depending on the size, the shape, we could have a different region of the plasmonic peak. You could see very nicely if we have the same nanostructure, just changing the material. For example, silver, mostly it's in the UV, in the visible region. The gold is near 500, 600 nanometers. And if we are combining them, making a coarser structure, we could do something between these two nanometer regions. So basically, the sensitivity and all these things could be varied. If we are varying the shape, for example, we could use different shapes, cones, different discs, different rods, different prism, and so on. And by varying the shapes and varying the size and the gap between them, we could a little bit influence on the sensitivity. And of course, we could characterize it. So basically, what we did in Debrecen, we created just the very easiest way. We cleaned and put on a glass substrate a layer of gold. Of course, we worked with silver as well, but this presentation focused on gold. So we put a layer of gold and we annealed it, and we get very nice nanoparticles. We could say nano-islands. You could see it was before the image, it was after it. We got a lot of nanoparticles because we were interested in how the layer thickness and how the annealing temperature and how annealing time has an influence on the processes what was examined. So basically, we have 2 different thicknesses, 4 different times, and 4 different annealing temperatures. So that's why it was a really huge job, because after that we made all the particles, we checked the SEM image. After the SEM image, we checked how the nanoparticle size looks like, and after that by NI Vision Assistant, we helped us, and after that by the MATLAB configuration, we find out the distance between them to find out the gap, because the gap in this because in these processes are very important. So basically it looks like this. So the results on the preparation of gold nanoparticles, as I mentioned, we checked 2 different thicknesses, 4 different temperature, 4 different times. So it's a lot of samples, and you could see that very nicely the thickness has a huge impact. Because by the thickness we could really vary the size and the gap. For example, it was 9, it was 10. We put one of the 10, but we didn't examine in the further steps, and we put 12, and you could nicely see that nanoparticles are smaller here, because and increasing the thickness it became larger, and the gap between them became larger as well. And you could see all these things. It has an influence on the optical spectra. So you could see that all the nanoparticles, of course, if it's shifting to the red region, and you could see here that increasing the thickness, the nanoparticle size will increase at the same conditions. I would like to mention it. It has 550 temperatures for 30 minutes. Okay, so the same the parameters we deal with. Okay, so after that we checked the sensitivity. So here the LSPR sensitivity. So LSPR sensitivity, we checked how the peak of the nanoparticles changing by changing the refractive index. So we measured the nanoparticles in air. After that, we measured in water, and we checked how this sensitivity will change. For example, here for this sample, you could see that it was approximately the delta lambda is 28 nanometers. So sensitivity was approximately 84 nanometer per real. And here we checked how the absorption peak was shifted by the size, and it's a well-known thing that by shifting, by increasing the size, the absorbance peak is shifting, so it's increasing, and it was a very nice result, it's a well-known result, of course. And after that, we checked the cells efficiency. We checked how everything happening with cells. We put first of all benzophenone on the nanoparticles. So first of all, we measured the reference on the glass substrate, and after that we put the same amount of benzophenone on the nanoparticles. We checked this peak approximately at 1,600, and we measured the enhancement factor like this. And we found out that a very nice connection between the size and the gap. But first of all, I would like to show you that we were happy because we had different excitation sources. So we checked how the excitation sources in this case has a role, and it find out that for the gold, of course, it come out that for the gold, the 532 nanometer excitation was the best. So after that, all the experiment was done by this excitation, and after that we checked how the size and the gap between the nanoparticles influencing on the surface and hence Raman scattering. And it's come out, it's well-known things that's increasing the size, it's getting larger, we get a larger effect of enhancement, and we get closer nanostructures, the closer packed things, we get much better cells things. And if we combining, so interparticle distance, so distance between the nanoparticles and the size, we're making a ratio, we have a very nice exponential result. And it came out that, so basically we could say that if you have a larger and closer packed nanostructures, we could have a larger cells performance, which is very nice. After that, we deal with two other analytes. We check rhodamine 6G and riboflavin, which are both are very usual analytes for cells. And we found out a very interesting thing that, for example, for rhodamine 6G, yeah, it was quite the same, that we used the same substrate. So you could see the same substrate. That's 532 nanometer excitation. We get a very nice result here. And however, for the riboflavin, something strange happened, because we got higher enhancement for 633. Why? Because it came out that two in chemical bonding and hydrophilicity, and because of it, the surface attachment of riboflavin was better, and that's why the shift of the plasmon peak was larger as for the rhodamine, and that's why we got a larger enhancement for 633. So it was interesting that not only the shape, the material, the size important, but very important to check the analyte, what kind of analyte you are going, or we are going to investigate in our research, because maybe for each analyte, optimal structure should be chosen or should be created, and after that investigated. That's why after that we created much more nanoparticles. We would like to optimize the technology, and that's why we checked what's happening. So we choose two thicknesses, or we choose only two temperatures, but much more duration of the annealing. And that's why we checked what's happening. So basically, if you're taking from a physical point of view, simultaneously two processes are going on the surface. First of all, there's a heat-induced surface diffusion, which is resulting some kind of nano-island formation, and the nano-islands by this becoming smaller but with closer. And after that, at some step, the heat-induced Oswald ripening coming, which is as a result of this Oswald ripening, the nanoparticles, the big nanoparticles eating the small nanoparticles, we could say, and that's why we will have much smaller number of nanoparticles on the surface, but they will be larger, and the gap between them will be larger as well. So these two things are a little competitive, and that's why when we're checking what's happening, you could see that here I just put the heat treatment time, and in the y-axis you could see that we have enhancement factors. So you could see that in the first few minutes we have an increasing, and after it's starting to decrease. Possibly somewhere here the Oswald ripening becoming more advanceable. So that's why bigger nanoparticles, even we will hit bigger nanoparticles, but you could maybe remember that the size has a linear function effect on the enhancement. However, the gap between the nanoparticles has exponential, so it's much more intensive. And we checked for both initial thicknesses, and for both initial thicknesses we find the same. So basically we have some optimal annealing time, annealing temperature, and initial thickness, and by this we could find out the best thing what we got basically. So we really go through all the things. The next step we are going to study with the silver, and maybe with silver gold nano structures together. So basically I would like to conclude my talk. We were successfully done silver and gold. I showed today the gold things. We put different thickness and different times, and it's come out that higher deposition thickness and shorter annealing times could lead to the larger SERS things. And we got that. We got the main strategy should be that we should increase somehow. Of course, we should be very careful with it, because if we will get very large nanoparticles, the plasmon peak could be shift to the infrared region, and in this case, it will be really not so efficient. And of course, we should a little bit decrease the interparticle separation distance between them by different annealing things. And now the next step, we are going to use all these things for sensing of biological materials, because our university is really large, and we have a very good connections with medicine institutes. So we are going to study different biological or medical problems, and we are happy that the medical persons are really open for this. Some people who were involved to this project were my PhD students and my colleagues from Budapest, and I'm very happy to be really sponsored by these different foundations. And I very thank you for attention, and I wish you very good, successful conference and good health, of course, in our time.
Thank you, Ismail, for your interesting talk. Maybe someone have a question?
Yeah, Istvan, do you hear me? I have a question. Do you use your nanoparticles for investigation of different biological molecules? For example, maybe you investigate some biological objectives as cells, viruses, or something like this. Do you using SARS effect for investigation, or maybe you plan in the future use SARS for investigation cells or viruses? Because now it is a very modern technique for investigation biological objectives.
Yeah, I'm partly hearing the question, but not so. So I would like to ask the technician or the leading person to help me to proceed the question.
I can repeat. Do you plan in the future use SARS method and your gold nanoparticles for investigation cells or viruses? Because now it is very modern technique for this subject?
We are going to study different biological particles, and maybe we are going to proceed in the direction of core shell nanoparticles, silver and gold, but it's not as easy to be honest. So
okay, thank you.
But yeah, so basically we are open, and we have different opportunities in this sense. So that's why I came here. Maybe we could find out some partners as well from your community to deal with the same topic.
Thank you so much. Any more questions? Please come here.
Hello, my name is Anastasia Mansky. Sure, while obtaining spectra, and how fast particles was cooled.
Okay, thank you for the question. So basically, the spectra was taken in air, so not during annealing. How it was done, the annealing, we have a argon gas closed chamber. So we put the pure glass with metallic layer. We wait a little bit. After that, we put to the chamber, wait 1 minute, 2 minutes, depending on the annealing time. After that, we take out. We wait till it will cool down, and after that, we take out from the chamber. So this is how it was done.
Okay, and was there any signs of crystallization or like
oxidation?
I'm interested. Was there any signs of some structure, like was it just droplets or any signs of some structure?
Okay, so basically, because the initial sequence, the time and the annealing temperature has an influence on we could say on the size and on the gap. So we didn't create any kind of other shape nanoparticles, and by these 3 parameters we could vary, we could change even the size, even the shape as well as a little bit. So as larger will be the annealing time, as more spherical shape-like will be the structure, or we could say the disc-like, because it will be pushed. So no, we didn't create any kind of rods, dike or something, but in the future we would like to make a core shell one.
Thank you. And as far as I understand, silver was just like the same like gold, or was there any differences when you?
Yeah, of course. More results I have on gold, but we already got some results on benzophenone for silver, and of course because the silver peak was much less, so approximately for 380 till 470, depending on the size and the gap. Of course, the excitation wavelengths was the best, the 488. So of course, but the main things that how the geometrical things influences on it, it was the same. We didn't examine any other analytes. We are going to do it during autumn. But yeah, you're right, because silver it's not so easy, because it's very easily oxidizing. So we should be very careful with it, and that's why we would like to cover it with gold, and maybe in this case we will get a better sensitivity. Yeah, so silver is a tricky point, because it's changing by time more easily than gold. So that's why it's if you did it, you just immediately should do your experiments.
Thank you very much.
Thank you for next questions.
Thank you for your questions. Unfortunately, we have to move on and invite the next lectures. Thank you, Istvan, for your interesting talk and interesting answer in the question. And our next speaker will be Martina Tupikovska.
Yes, I have.
Just a moment. To use the laser, you should press this one button.
Okay. Okay, thank you.
Okay, thank you. Let's start.
Good morning, everyone. My name is Martina, and what I'm going to talk about today is investigation of plasmonic nanoparticles, creating long-range ordered structures during crystallization process. My motivation to work on this research was understanding the process of crystallization of photonic nanomaterials, because it is of great importance for the design and model their properties. With that, it has a huge direct impact on development of future optoelectronic technologies that rely on such materials. While crystallization in the solvated environment has already been studied using ex situ methods, the crystallization in solid state switchable assemblies of nanoparticles remains so far unexplored. To fill this gap, today I will present proof of principle experiments on crystallization of thermally reconfigurable materials built from plasmonic nanoparticles that are excellent testing material to in situ and ex situ measurements. The first stage of my work was the synthesis of gold nanoparticles, which chose as a model material in this research. The synthesis was carried out according to a modified literature procedure, and as a result of such synthesis is a formation of nanoparticles in diameter about 4 or 5 nanometers, but unfortunately the size distribution of such nanoparticles is huge. We know from previous research carried out in our lab that the highest quality of self-assembly we can obtain for highly monodispersed nanoparticles. For this reason, I decided to subject my nanoparticles to the tedious fractionation procedure. And the hard work has paid off, because I obtained a really narrow fraction of nanoparticles, and the additional confirmation of their high quality is here, because nanoparticles create hexagonal structures. Okay, in the context of this work, the hybrid materials are built of a metallic core and its binary coating in the form of a mixture of thiols. To obtain such materials, I conducted my primary nanoparticles covered with the decanothiols to the ligand exchange reaction. Then some of
these short alkyl ligands was replaced with promesogenic ligands with the structure, and the structure is here. And the success of such a reaction we can observe, for example, on the TEM photo, because now we have not hexagonal arrangement of nanoparticles like before, but something like lamellar arrangement. And why it happened? Okay, because aromatic rings, being the part of promesogenic ligands, interact with each other at the room temperature and separate on the surface of nanoparticles. And the distribution of ligands on a single nanoparticles has the direct impact on the arrangement nanoparticles in the system. These short distances generated by short tiles translates to distances between nanoparticles within one layer, and these bigger distances are responsible for the distances between layers of nanoparticles. That's the reason we observe not hexagonal, but lamellar arrangement of nanoparticles with two characteristic distances between nanoparticles within one layer and between layers. Directly after drop casting on the substrate, nanoparticles are arranged isotropically. To put them in order, I have to conduct this material to thermal annealing. That is, I heated the material above the phase transition temperature and then cool it down to the room temperature. In order to determine the structure of the material, I conducted a small angle X-ray diffraction investigation, and the evolution of the signals showed that we have two distinct order phases. Below the phase transition, this is BCT phase, and above the phase transition temperature, we have BCC phase. Investigation of the hybrid materials in the room temperature, depending on the number of cycles of thermal annealing, proved that 2 cycles of thermal annealing results in creating bigger monodomains than in case of 1, but further increasing the number of cycles doesn't continue this effect. Another factor I took into consideration was cooling rate of the samples, and after analysis of TEM micrographs and after measurements, I proved that the size of monodomains increases exponentially with the decreasing cooling rate. Here I would like to show you my favorite TEM micrograph, and I believe that beyond the subjective beauty of this monodomain, the vast area this monodomain occupies is impressive also for you. Okay, until now we discussed either nanoscale ex situ measurements using TEM and bulk in situ measurements using SAXRD. But to fully understand the the measurements on single particles or ensemble level were required. After optimizing the procedure of obtaining our samples, we sent them to the Professor Sarah Balz from Belgium, and direct comparison of dark field photos confirmed for the first time that nanoparticles assemblies exhibit a structural response to the heating and cooling at low pressure in the TEM machine. Furthermore, tomography series allowed us to obtain 3D reconstruction of the selected part of our samples, and ortho slices through them show that nanoparticles in the samples are well resolved, and hence a quantification of the results is possible by analyzing corresponding FFT images. And FFT image for sample directly after the drop casting show single broad signal, which is characteristic for isotropic arrangement of nanoparticles. And after thermal annealing, we can observe long-range order of nanoparticles and direct signals on the FFT image. And they are connected with BCT phase. And the last question I asked was is it possible that we can manipulate the optical properties of the material by this condition of crystallization. And the answer to this question I obtained by UV-Vis spectroscopy. As you can see, there was differences in the positions of maxima of plasmon band, and it is obvious because we know that the position of plasmon band is really sensitive for the spatial distribution of nanoparticles. But another problem was that none of experimentally obtained spectra wasn't covered with this model one. And the question is why. And to explain this, we had to analyze another TEM photos, and we noticed that our domains aren't as perfect as we thought, because in their inner side they are perfect. They are creating perfect BCT phase, but and at the outer side parts there is isotropic. So that's the solution of the puzzle. The monodomains aren't as perfect as you thought, but perfect enough, I think. And here is the summary, but I think I should skip it. And thank you for your attention.
Thank you so much. Any questions? Please come here. So
I like to sit again.
unfortunately, we will be not able to hear you in the online translation. So please come here.
Thank you. So you have rather impressive results in obtaining monodisperse distributions of nanoparticles. How did you achieve this? You didn't quite told us the details. You didn't quite tell us the details.
Okay. So the solution of this puzzle is that I added the solvent which precipitates nanoparticles slowly. Small amounts of this solvent, and then centrifuge it, and the supernatant was okay. I take my supernatant to the different I don't know.
Fraction.
Yes, different fraction, and added next portion of this bed solvent which precipitate our nanoparticles. So not
under the constant centrifugation. Under steady centrifugation.
Yes, many times I added a solvent and centrifuge after it, but not a huge amount of this solvent, but a small portion.
Okay, thank you very much. Thank you so much.
Thanks, really interesting talk. My concern about you directed the self-assembly of the nanoparticle. Is it not only about crystallization? I believe the interactions between the ligands have something. Did you reveal this kind of interactions? Which kind what we have?
No, we haven't do it now. Till now, but I think that's a good idea.
Okay, why getting in lines, not aggregating in this sense? Because you're having a ligand cover the surface. I mean, the surface chemistry of the particles is almost the same. Why getting in one D structure?
You are talking about
lamella structure. You have a perfect lamella structure.
Yes, because this is because of the structure of ligand and the amount of molecules of this ligand on the surface. It depends. The structure of create monodomains depends on the amounts of chromosogenic ligands on the surface of nanoparticles.
Short question. When you compare optical properties of your ordered nanoparticles and disordered, yes, you have obtained very near the same result. But the question, how you measure it? You measure it from the large samples, or you try to use some microscopy, because you have different domains with different ordering, and you need to try to measure from the one domain, but not.
No, we are measuring in bulk, yes.
So maybe it's try to use to measure from the one domain, and you see some different optical properties. Okay.
Okay. Thank you so much. I have a great pleasure to invite next speaker, Professor Dmitros Snishko. Just a moment. Which one presentation is yours?
Yeah, that's right.
Yes. You know how to use the pointer? The laser is down there.
Yeah.
Okay.
Thank you. Good morning. I represent my university, Kharkiv National University of Radioelectronics, and my report about atomic force microscopy of laser-induced periodic surface structures. In this report, I briefly very short discuss about formation laser-induced periodic surface structure, atomic force microscopy modes to understand what I will show, and as sample for research we select glassy carbon material and analyze before formation and after formation lips structures, lips on glassy carbon, and we will do some conclusions from this report. So first one, laser-induced structures. This one enough new direction in formation of nanostructures. This very fast growth last decade with spread of femtosecond lasers, which use for these formations. For this one, use laser ablations and pulse mode when laser focused at the point on surface and point by point treat the surface. Formation of plasmonic resonance on surface create conditions for formation of periodic structure, which we will see a little bit later. Yes, of course, it's nano-sizing. For investigations, we analyze view samples. In our works, we try to find new electrode material for electrochemical applications. So specificity for our work, we create samples of these small parts which contain Teflon insulator, which inside contain rod from glassy carbon, and glassy carbon treated by laser for formation lip structure. At the left you see a bare glassy carbon without lip structure. At the right, at specific angle, we can see interference in film, in the film of which is laser-induced periodic surface structures. Next, a little bit about atomic force microscopy. This one, probe microscopy, which use cantilevers, work in interaction with surface and mechanical deformation controlled by a laser system. This represent contact mode when probe attached to sample, and we have repulsion forces between cantilever and sample. But in atomic force microscopy also present other mode. This one dynamic mode or typing mode, also known, which work at moment of attraction force formation between cantilever and the sample. This one a little bit other mode, which represent a little bit other mechanical properties of surface and possible obtain additional information about structure. So we use both modes for analyzing of surface and structures which we obtain. So one moment. First one, we begin from analyzing of bare electrode, and before analyzing we use polishing procedure to obtain enough flat structures, and as you see we obtain enough flat structures with variation in enough small range if our powder particle was around 30 nanometers. Cross section we see some structures which may be rest of this particle at the surface. We think that this one penetration to the material, and at first experiment we see this amount of particles correlate with time of next treatment with washing, with ultrasound and in different solvents. At the if increase scale for that axis, we see these particles. It's not so big, and in reality, on electrochemical properties, this effect not sufficiently influence. So we can use with this small amount of particles at surface of glassy carbon. Analyzing of heat distribution at the surface, we see this one in enough small range. Yes, of course, small angle distribution. So this one talk about enough flat surface at a small area of observation. When you see this one nanometers, so 500 nanometers per 370 nanometers, we begin see microcrystalline structure of glassy carbon. Yes, we know that this one should be as like amorphous, but in reality, small particles enough 50 nanometers we can observe as like small spheres, and this one nature of surface of glassy carbon. So it's also demonstrate normal distribution of heat. So it's talk about nature formation of this structure at the surface. Sorry. So next step, this one analyzing in dynamic mode. In dynamic mode, present possibility for analyzing also phase portrait, which is represent how to change oscillation of probe and use this one signal to form enough specific. If this one topography, which represent reconstruction of surface in dynamic mode by heat distribution, this one picture, it's a representation of phase variation of cantilever oscillation at the surface, and this one image obtained as a compilation of 3D profile, 3D image of topography together with skin on surface of phase image of oscillation, and we see this distribution enough uniform for surface and associate with topography. So we do not see specific variation in material mechanical properties on the surface. So this one enough right as glassy carbon enough uniform and doesn't show some specificity at some islands or something like this. So the next, this, yes, of course, lip structures. A specific lip structure on glassy carbon, that glassy carbon is enough unique material because at normal conditions we do not have liquid phase, and we have that solid material at high temperature evaporate, so we have sublimation of material, and as a result traces of laser treatment on surface represent these one big waves on surface. And as we predict distribution of laser power at the beam focused on the surface represent this variation in heat as like big waves on surface. Next, if you look more precise, we can see on the big wave, small waves. This one is result of formation of resonance, plasmon-phonon resonance, plasmon-phonon waves on surface, and represent how to treat laser on the surface. So we see, yes, of course, formation-specific direction on the surface which associate with big waves, but on the small area of observation, so this one 2.5 on 2.5 micrometer, we can see more precise ellipse structures which is organized on surface by laser treatment. So if take a cross section, this one marker line, we see this profile between two markers, and we can obtain numbers which characterize this surface. So periodic structure period is around 780 plus minus 5 nanometers. So this one, yes, of course, smaller than a laser which use for treatment. We use laser with wavelengths around 1030 nanometers. So heat of these structures between bottom and top around 250 nanometers. And we see good periodicity and reproducibility at the surface for these structures in all areas. So I represent only view images, but in reality we analyze this structure in different places of electrode, and we see that statistically this one enough good reproduce in many places of electrode. So the next step, yes, of course, this one also work in dynamic mode, and we try to analyze maybe laser treatment change mechanical properties of carbon at surface, and we have some different materials. But in reality, we do not see something specific, and variation in phase only associate with topology. And if we see nanocrystalline structures like small sphere, this one represent in phase variation also. So we associate phase variation only with morphology, and not is absent variation in structures. So this one little bit as magnifications is 20 by 20 nanometers. In dynamic mode also we obtain phase shift, and we have also enough uniform distribution, maybe not enough clear obtained phase image, but waves enough similar, and the variation with phase, it's a result that increase and decrease heat at the big wave. In my conclusion, we obtain by laser treatment enough good structures which will be in future used as electrode material. Investigation about this one will discuss my colleagues tomorrow, Yuri Zholodov. Properties of this material, electrochemical, and using this substrate for next fabrications as like sensor, electrochemical sensor. Bare electrode demonstrate enough good flatness with parameters, roughness parameters around for RR parameter 5 and RQ around 7 nanometers. We determine periodicity of structures and heat that is 250 nanometer and 765 nanometer correspondingly. Big wave period we see 14 micrometers. This one exactly according program of laser scanning track. Obtained result also before treatment and after treatment, roughness of surface sufficiently grows. Yes, of course, this one result of the treatment and formation of lips at electrode surface. So you see 100 time area of electrode sufficiently increase. Roughness of surface increase, so increase also work area of electrode. This one structure was obtained by our colleagues from Lviv company, Novi Nano Lab. Yaroslav Gnilitsky, leader of this firm, scientific leader of this scientific company, Novi Nano Lab, and our task was investigation of this new material and characterization and try to find application for this one. This work was supported by National Research Fund of Ukraine, project registration number you see. So thank you for your attention and please question.
Thank you for your talk. It was very interesting. And we have time only for one question, because we are a little bit out of time. So please, questions. Please come here.
Thank you very much for introduction. Thank you very much for your report, and I have one question. You told that you use your materials in electrochemical area, yes, as in electrochemistry. So the question is very short. Do you have the advantages of your materials when you use in electrochemistry? You told that you use in sensors. So are your materials have they excellent characteristics, or can you tell some words about your materials?
Thank you for your questions. It's enough interesting. It's not exactly about my report and maybe sufficiently closer to my colleague. I want say only one thing to save interesting to my colleague report. Really, after treatment, we see changes of electrochemical properties. How use this one? We have a few ideas, but about this one, we'll talk my colleague Yuri Zholkov tomorrow.
Okay, thank you very much.
Thank you for your question.
Okay, thank you for your talk, and we have to move on to the next session. Nanobiotechnology for healthcare, and the first talk will be Alina Polymer. No, it's not covered right now.
Just
Okay, before starting, my congratulations to everybody on the national feast of the formation of independent Ukraine. And thank you very much to organize committee for the honorable opportunity to make it report here about our investigation. One second. Okay, nice. It's a great problem of side toxicity of cancer drugs. Wait. And here we try to create anti-cancer drugs from two non-toxic components, nanogold and polysaccharides, from the plant microalgae. We know nanogold application in medicine. It's drug delivery system, diagnostic, physiotherapeutic methods. Their methods are not connected of therapeutic properties of nanogold directly. We prepare nanogold by Davis method, ethanol reduced. Last decade interest in polysaccharides in oncotherapy is activity growing, and different investigations demonstrate mechanism of anti-cancer activity of oligo and polysaccharides. Among them, complexation bivalent cations, activation of apoptosis and exhibition of proliferation, multi-resistance and metastasis. For chlorella vulgaris polysaccharides, exactly its stimulation phagocytosic activity, proliferation of splenocytes, and synthesis of cytokinase. It's very important for selectivity what polysaccharides of chlorella have toll-like for receptors for many types of cancer cells. We isolate and used polysaccharides from microalgae chlorella vulgaris, large 3. As we noted early, our interest and task to find and study possibility of direct application of bioconjugates from two non-toxic components of nanogold with polysaccharides as drug for cancer therapy. Size of poor nanogold, it's here. Nanogold with polysaccharides, it's around 25 nanometers. Bioconjugates, sorry, from two direct application, were studied by scanner force microscopy, electron microscopy, and UV-vis microscopy. Scanner, UV-vis, electron, and we optimal concentration for synthesis bioconjugates aurum polysaccharides was found from the compressed study of electrophoresis and adsorption polysaccharides or on nanogold. Every nanogold must be stability in blood because thrombosis problem. And polysaccharides protect nanogold against blood proteins absorption. Excuse me. This is its poor nanogold, and here nanogold, bioconjugate nanogold with polysaccharides. And poor nanogold is stable in plasma, sense to protein absorption, and invisible for cancer cells and tumors. Poor nanogold with saline immediately coagulate, because here don't have another one. And bioconjugates aurum polysaccharides are stable in plasma and saline, and may selectivity interact with cancer cells and tumors. Polysaccharides anti-cancer properties. Mechanism interaction of polysaccharides and nanogold study from Fourier transform infrared and Raman spectrum show interaction by carboxyl and carbonyl groups. The retained isolation symmetry indicates the existence of the chemical absorption bond metallic oxygen with the noted groups. The date of the MTT test separately for nanogold, nanogold it's blue, polysaccharides is green, and bioconjugates aurum polysaccharides it's red, and confirms the fulfillment of our original goal of work. It's like two practically not toxic components when combined in bioconjugate form and nanoform toxic to blood cancer cells. It's been much bigger. It can be assumed that this synergism is due to the catalytic action of nanogold on polysaccharides anti-tumor action. And we have different time, like 24 and 48 hours. Reagent trypan blue stains date cells. And this effect can be recognized from the first minutes of contact with the help of microscopy in the Gadolinium chamber. Therefore, is our laboratory using these methods. We carried out similar studies, but for this is 2 hours of contact, just 2 hours. At the same time, nanogold and polysaccharides are practically not toxic. Photos show rapid death of cancer cells. 50% of leukemia cancer cells, the Marva line, die after 45 minutes of contact with bioconjugates aurum pass. We have developed special colloidal complexes that included the study of heterocoagulation of cells with nano-object, the kinetics, heterocoagulation kinetics, and cytotoxical kinetica in the same time. The results show stronger interaction and toxical effects of bioconjugates aurum polysaccharides on UCAT cancer cells, red curve. Yes, and compared with the healthy lymphocytic green curve. Possible reasons polysaccharides properties that determine selectivity are not here. Cause of cancer cells death after bioconjugates aurum polysaccharides action was studied by the MTT test and the annexing test. Here it's like a healthy cells, and this is like cancer cells. For cancer UCAT and U867 cells, apoptosis and necrosis after the treatment with our PS was 201. For healthy BPM L and monocycle cells, this ratio was 1.501. It was shown that the result of contact of reaction oxygen significantly increased 1.501. For the reason of biodetection, we synthesized nanogold in the form of monocycles, nanoprism with mirror sulfides. Scanning force microscopy date. And we see line dimension and thickness. We show the mixture of cancer UCAT. It's more large. It's cancer cells and blood cells, like healthy cells. like cancer cells more bigger size than healthy cells. If we have time enough, I will show you our video about show you our sparkly crystals. Toxicity and selectivity of nanoforms with the same core composition are more dependent on the surface composition than the core shape. His conclusion is supported by the data presented here. Bioconjugates nanocrystals, aurum PS. This is healthy and this is cancer. Nanocrystals selective toxic effect on the viability of leukemia cells normalva and healthy leukocytes. This result of comparable to those demonstrate for quasi-spherical bioconjugates, aurum and polysaccharides. Do we need gold on the form of nanoparticles? Let's go from hard and soft nanodrugs. Polysaccharides complexes with ionic gold. We will show complexes with ionic gold and on normalva leukemia cells and healthy leukocytes. Here it's seen that the selectivity is preserved. Advantages, it's easy of preparation of polysaccharides combination complexes with ionic gold and no dangerous of thrombosis. And conclusions, bioconjugates from two non-toxical components, aurum and polysaccharides of microalgae selectivity inactivate leukemia cells. Death of cancer cells due to apoptosis. And it was being shown that polysaccharides complexes with aurum ionic converted and synthesis have a selective cytotoxic effect commensurate with the effect of bioconjugates aurum polysaccharides. Thank you for your attention, and please, if you have questions. Nie включать? Okay.
Question is, what was the mechanism of protecting of nano gold by polysaccharide? What was the mechanism?
We have like nano gold particles like mixed together and like polysaccharides adsorption on the surface nano gold.
Nano gold?
Yeah.
Just adsorption?
Yeah.
In what form adsorption?
What form absorption? Just
okay.
I mean chemical, physical. It's chemical, yeah.
Okay. Thank you.
Thanks, really interesting inside the cancers. My very naive question, which kind of polysaccharide you using?
Microchlorella vulgaris. Chlorella vulgaris, large 3.
Okay, high molecular weight or small molecular weight?
Say it again?
Molecular weight of the polysaccharide. It's a small molecular weight, very small chain of...
Oh, it's very big, excuse me, and I know, but I check. I can't... Можно мой телефон? Sorry, I forget. It's like, I know this, but... Maybe I answer after a few seconds. Okay, I find it and sorry about that. Any question? Yeah.
May I have a question about your complexes?
Yeah.
So we are.
Which one?
First of all, about this, the charge of your gold. Are you sure you have only +1 oxidation state, not +3? What are the physical methods? The charge of the ion.
I know about this. It's because gold have different valence. Yeah,
yes,
it's like 2, 5, 7, like different. But yes, it's 1.
what are the physical methods you can use to confirm this charge?
It's hard to answer you right now, and I just check after like 5 minutes after this is
okay.
about, yeah, and I can answer you. Yeah.
Okay, thank you.
I know your question, like, yeah, about this. It's interesting because why one? Why not three? Yeah.
Thank you for your interesting speech.
Thank you so much.
If any of you have some questions or comments, you please set and contact with our speakers. We are ready to proceed our next presentation by Dr. Anton Tkachenko, Kharkiv National Medical University, sample nanoparticles triggered effects on culturated dermal fibrillates. Please.
Okay, thank you. Okay, good morning, dear colleagues. I would like to present our joint project with the Institute for Scintillation Materials of the Academy of Sciences of Ukraine, which focuses on the evaluation of biological effects of gadolinium, yttrium, orthovanadate nanoparticles. So as you probably know, cancer remains a huge social, medical, public health, and actually economic burden worldwide. And radiation therapy is a leading treatment approach for this disease. Up to 50% of patients receive the radiation therapy either alone or in combination with surgery or, for example, chemotherapy. However, despite its obvious achievements, it has certain disadvantages, in particular toxicity to the surrounding tissues. And in order to avoid this toxicity, we can increase the local radiation dose using some radiosensitizing agents. And actually, in this case, nanomaterials can be helpful. In particular, it has been demonstrated that gadolinium, yttrium, orthovanadate nanoparticles can be either antioxidant or pro-oxidant depending on the conditions in the cell-free systems. In particular, there is strong evidence that after exposure to UV light, these nanoparticles can generate reactive oxygen species and can show pro-oxidant properties. So that is why actually the next task is to assess how do they affect the normal cells. So the aim of this study was to assess how these nanoparticles affect the viability and metabolic properties of cultured fibroblasts, as well as the generation of reactive oxygen species in leukocytes. We used both UV light activated and non-activated nanoparticles. So a little bit about approaches that we used. So cultured skin fibroblasts were incubated with different concentration, you can see, from 0 micrograms per milliliter to 320 micrograms per milliliter. So we used both activated and non-activated nanoparticles. So using a phase contrast microscopy, we evaluated the monolayer of fibroblasts, and we used the MTT assays and neutral ray uptake assays to assess the viability and metabolic activity of cells. So what we observed? Low concentrations of both activated and non-activated nanoparticles didn't affect the confluence of the monolayer and didn't affect the adhesion of cells. The effects started appearing when we use a concentration of 80 nanograms per milliliter. So here you can see it's important to note that the effects of UV light irradiated nanoparticles were more pronounced compared to the untreated ones. The same trend was observed for higher concentration. You can see the adhesion is lost and the confluence of monolayer is lost. As for the highest used concentration, the difference you can see was not very significant between irradiated and non-irradiated nanoparticles. Here are the results of the neutral red uptake assay, which is used to assess the viability of cells. There was no statistically significant differences in this parameter, so we can make a conclusion that none of the concentrations of nanoparticles we used, both activated and non-activated, can affect the viability of normal fibroblasts in culture after 24-hour incubation. Here are the results of the MTT assay, which is used to assess both viability and the metabolic activity of cells. So the metabolic activity was higher after the use of 80 milligrams per milliliter of micrograms, of nanoparticles. And also we observed the statistically significant difference between UV light exposed and non-exposed nanoparticles when the concentrations were 160 and 320. So it means that when the high concentration of nanoparticles were used, the metabolic activity was high in cells exposed to the activated nanoparticles. And the next step of our study was to assess the generation of reactive oxygen species in leukocytes, because actually this is exactly the thing that is important in this case. They have damaging effects on tumor cells, this reactive oxygen species. So generation of reactive oxygen species was observed in leukocytes after 24-hour incubation. And for these stoppers, we used a common reactive oxygen species sensor called difluorodihydrofluorescein diacetate. And we used actually flow cytometry, this method, to assess the redox state of leukocytes incubated with nanoparticles. What is the principle of this method? Actually, this dye penetrates inside the cells, you can see, and inside the cells, under the influence of intracellular esterases, it undergoes deacetylation, forming DCFH. This DCSH is still non-fluorescent. However, when it interacts with the reactive oxygen species, it is converted to highly fluorescent DCF, which is detected by the flow cytometry. And exactly the intracellular concentration of reactive oxygen species is proportional to the fluorescence of this dye. So, blood was incubated for 24 hours with activated and non-activated nanoparticles at the concentration from 0 to 80 micrograms per milliliter. And after that, we obtained the suspension of leukocytes, and we used two markers, CD45, which is a marker for lymphocytes, in order to distinguish lymphocytes. So you can see here the gating strategy for identifying leukocytes. So here you can see the population of CD45 positive cells, as leukocytes. And then cross generation was assessed in viable cells. So in order to distinguish viable leukocytes, we used a dye called 7-aminoactinomycin D. So it can penetrate inside the dead cell, because usually the integral membrane is not permeable for this dye. So it becomes fluorescent only after binding with DNA. And if the cell is alive, if it is viable, this cell is 7-actinomycin B negative. So you can see here, after identify the population of CD45 positive cell, we identify the population of viable leukocytes. It has 7 aminokinomycin D negative cells. And inside this population, we assess the mean fluorescence intensity of this dichlorofluorescein, which is produced from the initial dye under the influence of reactive oxygen species. What did we observe? That the low concentration of non-activated nanoparticles, they didn't affect the generation of reactive oxygen species, while the activated ones, their action statistically significantly increased production of reactive oxygen species, leading to the development of the so-called oxidative stress. While the highest used concentration, 80 micrograms per milliliter, both activated and non-activated nanoparticles increased, so led to reactive oxygen species overgeneration. The same trend was observed when we gated the population of leukocytes with the highest generation of reactive oxygen species, probably neutrophils. So you can see the representative histograms that demonstrates our result. And actually, we can make a conclusion that these nanoparticles, they show low toxicity towards normal cell when used at high concentration, and the activated nanoparticles or pretreated.
Any comments or questions?
Thank you very much for just one simple question. If I understand properly the essence of your experiment, so you are pretreating your nanoparticles with light, and then you use them for reactive oxygen species generation and biological treatment. Is that right?
Yeah.
So the question is then, what is the nature of this activated state? Is it some triplet, long-term stable state, or it's some defects on the surface which are trapping some charge? What is the nature of this excited state of the nanoparticle?
Thank you for the question. Actually, these nanoparticles were kindly provided by our colleagues from the university, and I have a medical background, so I can hardly answer the question. But I believe that these effects are associated with the difference in the vanadium oxidation number. Yes, so 4+ and 5+, and due to that, electrons can move, and it can lead to the generation of reactive oxygen species. So from my medical point of view, actually, maybe I'm not right, no, I guess something like that.
Питання там є.
Is it okay?
Yes, I can hear you, please.
Thank you very much for your talk. It was really nice and brilliant talk. I have a question about some chemical aspect. Have you tried to do the comparison of nanoparticles without europium and with europium? Is any difference in Rose generation? Probably europium is also connected with this activity.
Probably yes, but actually, as far as I know from the previous results of my colleagues, there was no very significant difference. Yes, probably you should rather contact them, but as far as I believe, there is no very pronounced difference in this case, because as I mentioned, maybe vanadium contributes the most to such effects.
I'm sure, as a chemist, that the role of europium, it's a very expensive element, so introducing its cost. So I think it is responsible for luminescence. And when you illuminate your particles, they are shining with red color. I think this color is also one of the important issue which is affected by Ross generation and so on.
Thank you for this new insight. I guess we will use it.
Thank you.
Thank you.
Thank you very much. The next presentation to be given by Professor Andrei Netreba, Taras Shevchenko National University Faculty of Radio Physics, Electronics and Computer System, proton magnetic resonance response, real state. Please.
Good morning, dear colleagues. My name is Andrei. I am in this scientific research was carried out on the Department of Medical Radiophysics with cooperation with Institute of Neurosurgery of Ukraine.
To turn on the laser, press here. It's
different type. You can see magnetic resonance image weighted by spine density, weighted by spine lattice relaxation time, and weighted by spine relaxation time. You can see that different of these images have different specialities and particulars. For example, magnetic resonance images weighted by spine density shows the anatomical structure in general, but magnetic resonance images weighted by spine or spine lattice relaxation time is more informative for analysis of lattice relaxation time. The base of magnetic resonance imaging is to obtain specially distributed phenomena of nuclear magnetic resonance. For example, for obtaining signals, we can use spine echo sequence, in which this sequence consists from the radio frequency pulses for coding and magnetic gradients pulses for transverse gradient magnetic pulses for coding of special localized nuclear magnetic resonance phenomena. We analyze for this research magnetic resonance images for human brain and for human food. You can see that for different biological tissue, spine parameters such as spine relaxation time or spine lattice relaxation time is different, and thanks to these differences we can analyze different type of biological tissue by different methods. For gray matter, white matter, and special state as human brain as edema, you can see the value of these parameters. And magnetic resonance reconstruction weighted by spine density we can obtain by using parameters of magnetic resonance edema, maybe recognized or high resolution. Also, in medical in magnetic resonance imaging, other methods with post-processing, with filtration, reconstructed images. You can see that quality of these images may be as low and high. For example, in center part, quality may be high if center part is interesting for this diagnostic.
Therefore, it becomes relevant to study the state of male fertility functions in patients with chronic kidney disease, which treated with nanocomposites. The research focuses on the further study of the new effects of the hybrid nanocomposites based on branched copolymers of dextran polyacrylamide in anionic, so-called DGPAAPE form, with incorporated gold nanoparticle. In particular, on reproductive function using male mammals, namely here is mice, under conditions of experimental chronic kidney disease, because it hasn't been studied before. We used the copolymer in anionic form, DGPAPE, as a polymer matrix for in situ synthesis of gold nanoparticles here. And it consists of dextran core and 5 grafted PA chains. The anionic copolymer was prepared by alkaline hydrolysis. Parameters of this polymer and the processes of synthesis of gold nanomaterial 20 nanometers in size and have spherical shape. The treatment of anionic polymers separately and with intercorporated gold in the tail vein of the animals in 0.3 milliliters once a day 5 times. The administrated dose coincides with the principles of the conversion to the doses of humans. You can see here the TEM images and the size nanoparticle distribution in gold zones synthesized in anionic solution. Our experiment were in 2 series. On albino white laboratory mice weighing 25 till 30 grams. Experimental chronic kidney disease was reproduced by 8. Amount of protein in animal urine has proven kidney damage. In the first series of experiments, we evaluated the by light microscopy. First, sperm concentration and the number of abnormal forms of sperm. Second, the ratio of cells of different generation of spermatogenic epithelium in the testes. And using fluorescence microscopy, we calculated the number of the living, apoptotic, and necrotic cells of the testes, such as primary type of fertile qualities of males, by under condition of coupling with the intact females. Due to estimation pre- and post-implantation of embryos of live per female. Result. In group experimental plus treatment composites, we observed the most damaged effect here. A decrease in the number, an increase in abnormal sperm, and those with the primary in comparison with the such value in the control conditions of treatment with nanosystem in the case of experimental kidney disease. Condition of experimental kidney disease, a decrease with this value in control and polymer separately were registered. But the observed in the experimental kidney disease plus gold nanocomposites group. A decrease in sites compared with this value in the control and under the treatment of gold last row. Left picture. Changes in the generation of the testicular cells, so-called primary spermatocytes, were observed in animals with experimental kidney disease with treatment of the gold nanocomposite, an increase in the value of pre-implantation motility of embryos in comparison with such value under condition of kidney disease separately. In publications of 2017, we found the interesting evidence. And pre-implantation death can be associated with genetic disorder. This concerns sperm tail abnormalities. According to our research, 5-type treatment introduction of the gold nanosystems under condition of experimental chronic kidney disease leads to the probable increase in pre-implantation mortality of embryos, which may be caused by an increasing number of sperm with tail abnormalities. Generally, we can say treatment with such nanosystem of gold are not critically dangerous for therapeutic use, even an initial stage of chronic kidney disease. Thank you for your attention.
Thank you. Questions, please. Thank you very much.
Thank you.
Now we proceed to the next part of the section. The next presentation to be given by student Oksana Chernyuk, Chico Institute of Surface Science. Synthesis and catalytic properties of nitrogen-containing carbon nanotubes. Yes.
Як можна користуватись?
Як тут користуватися?
Щас подивимося, тому що це не моя лінійка. Щас поїдьте.
Зараз
11, 11, 15, теж?
так.
Треба... Зараз собі об'являть.
То що?
Краще кава-брейк, ми поки що приготуємо все, да? Як розберемося з лінієчкою, з всіма, навірно, краще...
Nav coffee break.
Давай.
Да. Будет модератор. Он здесь уже в зале.
Добре.
турбуйтеся, я знову об'явлю. So we begin our conference, continue, and this section, nanocomposite and nanomaterials. The next speaker is Oksana Chernyuk from Chuiko Institute of Surface Chemistry, National Academy of Science of Ukraine, with report synthesis and catalytic properties of nitrogen-containing carbon nanotubes. So, please.
Dear participants of the conference, I am pleased to present you our investigation fulfilled in Institute of Surface Chemistry in collaboration with our colleagues from Ningbo University of Technology. The work is devoted to synthesis and catalytic properties of nitrogen-containing carbon nanotubes. Carbon nanotubes are found to show catalytic properties. Additional treatment, namely crystallization and doping with heteroatoms, modifies the carbon nanotubes electron system, facilitates the electron transfer, and this way increase the oxygen reduction reaction. Carbon nanotubes were synthesized by catalytic vapor deposition with previously developed technique. Nitrogen-containing nanotubes were obtained by a similar method by precipitation with gas phase using 100% acetonitrile and mixture of ethylene plus propylene at the temperature 750 Celsius on aluminium iron molybdenum catalyst. A possible growth process of nitrogen-containing nanotubes are present on this scheme, on this slide. One sample of initial carbon nanotubes here were oxidized by nitric acid and followed by impregnation with urea at the temperature 700 Celsius. Figure 1 present transmission images obtained product from acetonitrile and ethylene. As can be seen from these images, this product have bamboo-like appearance, characteristic of nitrogen-containing nanotubes. The structural state of carbon nanotube specimens were characterized by the Raman scattering method. The Raman spectra of nitrogen-containing nanotubes and initial nanotubes are presented on figure 2. The intensity of the spectra drops sharply. The main parameters of characteristic bands are presented in the table 1. As you can see, the frequency D for both samples of the band higher than for initial carbon nanotubes. Similarly, the frequency G for the samples increase compared to initial carbon nanotubes. This indicates a strong tension of the carbon nanotube lattice, which can be understood if atom of nitrogen embedded in the body of carbon nanotubes. The half width of the bands increase considerably, which indicates a significant disorder in the structure of this product. From the analysis DTA diagrams depicted on figure 3, you can draw a conclusion that intensive oxidation of nitrogen-containing nanotubes begins at 100 Celsius earlier than for initial carbon nanotubes. However, the heat capacity of this process is significantly higher than for carbon nanotubes. Presentation absent, I'm sorry. Yes, thank you much. To determine the chemical composition of carbon nanotubes, the method X-ray photoelectron spectroscopy was applied. As a result, the spectra of nitrogen-containing nanotube are present in figure 4. According to the obtained results, which show table 2, treatment of oxidized carbon nanotube samples with urea leads to a PR about 0.6% atom of nitrogen in their structure. Despite the fact the vast majority of nitrogen atoms are on site surface of carbon nanotubes as well as located along the surface. When modified carbon nanotubes by directly introducing ethylene diamine and acetonitrile in liquid state into stream of argon and hydrogen carrier gas, we observe and increase the number of nitrogen atoms embedded in the structure of nanotubes. For example, when we use a precursor as acetonitrile, we can see increase atom of nitrogen 5 times. When we use ethylene diamine as a precursor, we can so increase atom nitrogen in body of carbon nanotubes in 7 times. From the above data, it can be seen the indirect synthesis of nitrogen-containing carbon nanotubes, not only total content of nitrogen atoms, but also the proportion of pyrolytic and quaternary nitrogen increases significantly, against the background of a significant decrease in the amount of pyridinic form. This can be explained by the fact in direct synthesis nitrogen is uniformly distributed over the entire volume of carbon matrix carbon nanotubes. And urine nitrogen of carbon nanotubes with urea predominantly is the surface layers and near defects. From the data obtained during the catalytic decomposition of hydrogen peroxide of initial and nitrogen-modified carbon nanotubes, the reaction rate constant and affinity coefficients were calculated at different pH solution. Based on this data, the corresponding dependencies were built in figure 5. The given dependencies show that for all pH values, nitrogen-containing carbon nanotubes show greater activity in catalysis of hydrogen peroxide decomposition than unmodified tubes. The catalytic activity rapidly increases with increasing in the content of nitrogen heteroatoms of the body nanotubes. It should be also noted that nitrogen-containing carbon nanotubes reach their maximum catalyst activity with pH 7. Summarizing, our team's success to apply the method of the direct synthesis of nitrogen-containing nanotubes to obtain more catalytically active carbon nanotubes contain a large amount of nitrogen, predominantly the pyrolytic and quaternary type. It was found that the maximum catalyst activity is decomposition of hydrogen peroxide is observed at pH 7, regardless of the synthesis method. Thank you for your attention.
Thank you for your report. Please, questions? Yeah, please.
Have you some data about nature of nitrogen-containing groups, some structure of this environment? Which type of functional group you have in your nitrogen containing?
Okay, we haven't found present functional group because we incorporate heteroatoms, for example, nitrogen in carbon nanotubes with two methods: direct synthesis and with urea. So, and functional groups, it wasn't. We didn't take this issue into account.
And second question, have you some data about basicity of such materials, basic properties? As base.
Як основа.
Да. Основні властивості.
Yes, of course, there are many information. This information was researched before us, and they explain the basic properties of nitrogen contained carbon nanotubes. But in our case, we research the constant of velocity.
Thank you.
Thank you very much for your question.
Next questions, please. If we do not have, thank you again for report and questions. Please, the next report, Dr. Anna Potapenko from Joint Department of Electrochemical Engineering Systems. With report electrochemical characteristics of silicon oxide with water-soluble binder for new generation of LIB.
Just a moment.
One moment, please. So please.
Dear ladies and gentlemen, let me introduce my report entitled Electrochemical Characteristics of the Silicon Oxide with Water-Based Binders for New Generation of Lithium-ion Batteries. So I want to start my report from the introduction of the polymeric composition for applying in electrode materials for creation of the new generation of lithium and sodium ion batteries. It's interesting that lithium ion batteries are very popular now because they're used in much areas of our daily life for consuming electronic devices, for electric vehicles, and the development of the electrode materials and composition for the batteries is very urgent task now. So first of all, I want to tell that the polymer composition are used in lithium-ion batteries for preparing the electrode mass. The structure of these polymers is different. First of all, I want to tell that pay attention of the three classes of the polymer structures, materials for the electrodes. So you can see on the slide here the three main types. So is the double stent polymers and its branches and the cross links. So they have 2D and 3D construction. The next, I want to pay attention on the some main types of the polymers for preparation of electrode mass, and the next step is the battery, completed battery. And the main polymer composition for using for electrode mass preparation is a PVDF. it's not secret that PVDF is a polymer which used not only in electrochemical for electrode preparation, but in some other areas. But now I want to tell shortly about these binders. So PVDF, due to the unique structure and their plastic parameters, good plastic parameters used for the electrode mass preparation. But it's the main problem for using this polymer composition. It's not secret that for using this polymer, we also use the NLP solvent. It's not environment friendly, and when we use this solvent, it's not good for human health. So the problem of using this binder is urgent, and we should solve this because we should develop the other binders for using in batteries. So the next class is the SBR and KMC and LA types of binders. So SBR and LA structures have the important difference from PVDF. They're first of all good electrochemical properties in combined with active material, and their mechanical stability, and the main parameter is the low cost and environment friendly for the when use these materials in preparation of batteries. The next slide shows us the physical chemical parameters of the binders, because it's very important characteristics in the manufacturing of the real commercial batteries, because there are so many tests before these batteries will be used. So you can see these parameters for water-soluble binders, which we use, but not widely in Ukraine now, because now it's a great problem. Some researchers should test these binders before they can be used, but in the world they are very famous to exchange the very expensive PVDF on the other environment-friendly composite polymers binders. The next slide shows us the view of electrode mass for the battery preparation. Is the commercial is a view of the commercial batteries and commercial electrodes, and it's show us the mechanism of the coating of the foil, which coated by the active materials. And this slide show us that it's not so great difference between the consistent of the PVDF electrodes and water-soluble binders in compared with the standard electrodes. So it means that it's really potential perspective for using in a battery. So it's great exchange, we think, and many researchers and companies in the world begin to use these binders. So what's the problem of using these binders for concretic, for silicon oxide electrode material? Oh, sorry. So the silicon oxide anode materials is very famous for using in lithium and sodium ion batteries. But the great problem is the volume expansion of the particles of these materials, because the volume expansion is more than 400%. It's a really problem because when the electrode materials is cycling, after the time it begins to destroy. So we should solve this problem and find maybe some binders which can help to make the particles stable. So this is the view of the different ways for preparation of silicon oxide nanoparticles for application in the battery. So this method includes the CVD and etching the particles of silicon for creation of the special core for covering the particles, because they should be cracked. It's the main characteristics, and some methods which I will pay attention. These methods try to use in the commercial batteries, because I pay attention at this moment, because our electrochemical orientation must have the practical view and the practical results, because some electrode materials which study many researchers, but they not all use for really lithium ion and sodium ion batteries. So this is the scheme which introduced us the way for creation of the special bonds between the silicon oxide particles. So you can see that the main way is the creation of the oxygen bonds between the silicon, and these bonds are very strong and they can't be destroyed upon cycling. And there are, I think, the main way, but there are other. But in this work, we present this way for covering of silicon oxide nanoparticles. So is the really test of the battery, which consists of the LFP, cathode materials, lithium iron phosphate as the active material, and the water-soluble binder. And you can see that the efficiency of using the water-soluble binder is very high. And this is the real characteristics of the batteries for the commercial battery. So it's not prototype, it's the real working system. So I want to tell that the main parameters for the battery is the cycling rate. So how many cycles it can be work without destroying. Because every time we use our technique, our computers, laptops, and others. So we maybe not pay attention on the how long our device can work. But this graph demonstrates us this ability of using the very safety binders composition in comparison with the standard. Other slide demonstrate us the main electrochemical parameters. I will stop very wide on this slide, but only want to tell that the main advantage of the using of this water-soluble binder is the high resistance of the system and the high Coulombic efficiency upon cycling. What does it mean? It means that your battery can work a long time, because Coulombic efficiency will depend on the time. And another parameter is resistance, because if the resistance is very high, the battery will destroy it very quickly. And the next slide shows us some ways, several ways for improving the stability of silicon oxide electrode. So first of all, first is the creation of composite materials using the nanoparticles, including the way for creation the porous structure. It's very important because this structure can be stable and the batteries can endure the very high current loads. And then another way is the optimization of the electrodes by the using, for example, as I shown before, using the very high efficiency binders, and it's really improve the parameters of the batteries. And this slide shows the real results for the batteries, which consist the LFP active material. And it's very, we can see that the Coulombic efficiency of these batteries is very high. So it's really very important, and we can use this water-soluble binder very wide for the creation not only lithium-ion batteries but sodium-ion batteries too. These graphs demonstrate us the resistance in the system in our batteries. So you can see that resistance is very low. So it shows that these batteries are very effective using the water-soluble binder. And this also demonstrates us the resistance of solid electrolyte layer on the cover of the electrode. It's very important parameter because it also shows us the information about the ability to destroy, to degrade of the electrode materials. So these tests are very important. So they show us this, the water-soluble binders are very, very effective. The next slide demonstrates us the change characteristics electrochemical upon cycling. And this slide demonstrates us that combination of the different types of water binders, for example, LA136 with KMC is very effective, so these batteries have a very high efficiency upon cycling. And I want to pay attention that it's very interesting that only combination of these two binders can give us the very good results. So not pure KMC, not pure LA136. Because we did the investigation in this area too, I don't present these results now, but I want to tell that this combination is very effective, it's really good. And in the conclusion, I want to tell that the water binder include the composition LA136, which have a very strong polar groups which can connect with silicon and create the very strong bonds between the porous spheres, can be very effective for using in lithium-ion and sodium-ion batteries in the future, and they can be changed very easy on the very expensive and not environment-friendly binders, for example, PVDF. Thank you for your attention.
So thank you for presentation, and please question. So no questions, so I ask you, if you can please open a slide with analyzing of Coulomb efficiency first. Where, yeah.
Sorry.
Oh, yeah,
sorry.
previous.
Next.
Yeah, this one. We see that first tens, maybe cycles, small growth. Could you comment this behavior?
I try to comment because the test for commercial batteries. So it's really big battery which use, and I think that sometimes is drag effect because when we use water soluble binder, they really the Coulombic efficiency is more higher than we use PVDF, because very strong bonds create very easy and very quickly. But you see that when you cycle long time, the Coulombic efficiency is little bit low. So the advantage of these binders is firstly they create very strong bonds, but after that the mechanical properties of the electrodes is a little bit changed upon cycling. So I think it's not a problem. I think it can be solved, but this behavior is due to the strong bonds between the silicon and binder.
Okay, thank you. I think also it's not problem, but it's enough interesting behavior. Okay. So thank you for report. Please, next report, this one online report. Professor Pavel Sikora from Technical University of Berlin. Nanoengineering cementitious composites, perspectives of advanced functional materials. So, Pavel Sikora, are you here? Pavel Sikora doesn't connect to us, so maybe later. So the next report by Professor Igor Stolyarchuk from Drohobyczy, Ivano-Frankivsk State Pedagogical University, with report Magneto-optical characterization of cadmium magnesium telluride micro and nanoparticles. That's right? This one. No. Igor Stolyarchuk. This one. Yeah. Okay.
Okay. Mr. Chairman, ladies and gentlemen, time of lunch is very near, and I will be short.
But we have time.
In attention, I present results of studies of Magneto-optical properties of CD mangan tellurous micro and nanoparticles, our scientific group. Few my moments will be present in presentation, introduction, technological aspects of obtaining samples, micro and nanoparticles, optical and magneto-optical properties, and summary. In recent decades, the diluted magnetic semiconductors have attracted to the unique properties and possibility of their application in optoelectronics and atomic devices. The basic semiconductor where the cation, it's Professor.
No, continue.
Where the cation site is in the host matrices, lattices are replaced by transition metal atoms. My future is the strong SPD exchange interaction between band caryons and the magnetic ions, which results in the large diamond splitting, giant Faraday rotation, and magnetic polarons formation. It is obvious that when we go from the bulk materials to zero-dimensional structures, the mentioned magneto-optics phenomena should be modified by the strong confinement is all three-dimensional. Developed in recent years of new nanofabrication process have led to a wealth of novel engineering nanostructures with tunable size and shape parameters providing researchers with unprecedented control over their electronic, optical, and other properties. Many physical and chemical methods have been developed to synthesize a variety of the nanocrystals. Compared to the conventional chemical methods, the technique of the pulsed laser ablation of the solid target in the liquid environment has differently many advantages. This method is simply, and the nanocrystals produced by laser ablation in liquids are clear, don't have catalyst and other complex chemical reactions. For our experiments, we use two lasers, XMR and neodymium aluminium granate, with parameters present in here in table, and schematic diagrams obtained nanoparticles in colloidal solution or foil as substrate. Ablation process duration typically is 40 minutes in room temperature and high atmospheric pressure. Scanning microscope images presented here was used to analysis of fabricated nanostructures. The image confirms the formation of particles with different size, and both we observed as isolated nanoparticles and their agglomerates. The average diameters of the isolated particles is estimated to be range of 100–500 nanometers. Surface analysis shows morphology obtained micro nanoparticles. The image of nanostructures demonstrates the variation of size distribution of the nanoparticles without details of their shape and structure. Estimated from this IFM images diameter, the particles is in the range of 200 or 500 nanometer. Decrease the dimension of the research system for 3D to 0D leads to a radical restructuring the energy spectrum. This is most clearly manifested in when observing the optical spectra of nanostructures. The figures show the absorption spectra of investigated samples obtained by laser ablation. Green lines, and ball milling methods, blue line, and for comparison, some graphs show data for thin films obtained and prepared by pulsed laser ablation in liquid with similar content of magnetic impurity. As we can see from the figure, we observed blue shift of the fundamental absorption edge cause the quantum confinement effects. The exciton structure in this spectra under study was not observed due to the particle size distribution. This is especially evident for nanostructures obtained by ball milling methods. In applied magnetic fields, with the increase of magnetic strength, the absorption edge undergoes a shift towards low energy side, which is explained by the manifestation of the exchange interaction of localized spins of the magnetic ions with electrons or holes of the conducting and valence band. This is more clearly in the study of photoluminescence spectra. Photoluminescence spectra of nanocrystals with mangan contents of 10%, showing this figure shift on the structure the toward low energies and decrease with the widths of the photoluminescence band has been observed. The performance studies of the magnetic field dependence of the absorption and photoluminescence spectra demonstrates the transformation of the behavior of magnetic subsystem mangan to pulse ions in the nanoparticles. As the low mangan contents in less 0.05, they shift have linear behavior, and with increase of mangan contents we observed behave similar the two quasi-dimensional system of these materials. This behavior is evidence of the increases of the antiferromagnetic interactions, this linear dependency behavior of the with low mangan contents. Is antiferromagnetic interaction of mangan 2 pulse ions is the DD exchange interaction, as well as localized mangan 2 pulse ions with spins with exciton and holes of the valence band in zero-dimensional structures. As a further increase of SPD exchange interaction leads to increases the internal effective magnetic fields and the average magnetization of the subsystem. Such increase leads to the maximum spin polarization of holes and causes polarization of the magnetic moments mangan 2 pulse ions, which leads to the observed saturation effect in magnetic field dependence. The analysis of the concentration dependence of half-wise of the maximum photoluminescence band and Zeeman splitting confirms this assumption. The half-wise of the line grows almost linearly with increase of contents mangans. However, areas of content mangan in less than 0.05 then and is grade 0.05 is different. A similar behavior is observed also for Zeeman splitting. In concentration runs is less than 0.05. This behavior results of the exciton spin relaxation, despite the speed of increase of the spin temperature on manganese ions. With further increase of manganese concentration is contribution to expansion due to the excitonic magnetic polyron formation. Another interesting feature was discovered while we studying the dependence of photoluminescence intensity of the polarization direction sigma pulse and sigma minus. In the extramagnetic field requires 7 Tesla, it is impossible to establish the complete polarization of the transition as we observed in bulk materials, bulk crystals, for which degree of the polarization is equal to 1. In general, the degree of polarization is given by equations. In our experiments, with interval of concentration mangan of 0.05 to 0.15, we observed degree polarization approximately 0.6. Similar trends was observed experimentally of group Professor Gemelin for other reduced magnetic semiconductor nanoparticles CD mangan SE and for nanoparticles prepared by molecular BM epitaxion. This behavior is due to the mechanism of the spin lattice relaxation of excitons with enhanced with the increase of spin-spin exchange interaction in zero-dimensional semiconductor structures. Other magneto-optical very interesting effect is the Faraday effect. Is very interesting this effect for study magnetic subsystem in these materials as enhancement of this Faraday rotation is mainly associated with the strong SPD exchange interaction and also DD exchange interaction. The present study of Faraday rotation or Faraday effect were carried out in Yuri Fedkovich University National University in Ukraine. Spectral dependence of the Faraday rotation present in this figure came first corresponding nanoparticles of cadmium Cesium and T and KEV2 corresponding is composite films nanoparticles with polyvinyl alcohol. My future for the samples as negative sinks or negative sink of the angular rotation as for bulk materials, crystals, and additional enhancement of Faraday rotation by using evoluting approach Verded constant for nanocrystal is the order of magnitude higher than for bulk crystals. This enhancement can be a segment in the increase of oscillator stage of the excitons with left and right circular polarization and their difference in the external magnetic fields. Study Faraday rotation or Faraday effect in nanocrystals at helium temperature revealed two potential futures. Measurement in strong pulsed magnetic fields up to 20 Tesla showed that the Faraday rotation angle for the nanoparticles varied linearly in this range, and due to the antiferromagnetic interaction near the DD interaction mangan 2 pulse ions. Contrary for the behavior for the bulk crystals. Okay. Another feature was relevant in the study the temperature dependency of the Faraday rotation and transition of the diluted magnetic semiconductor materials from paramagnetic states to the spin glass states. As a fixed wavelength, we determine the temperature dependency in range of 4.2 Kelvin to 30 Kelvin. The procedure included initial cooling from room temperature to temperature 4.2 Kelvin in the absence of the magnetic field, subsequent application of the field in this temperature, and measurement of temperature dependence of Faraday rotation angle. During gradual increase of the temperature to temperature maximum 30 Kelvins. In second cycle of the measurement, the angle of rotation was recorded during cooling of the T maximum 30 Kelvin to the T minimum 40.2 Kelvin. We thus determined the typical dependence of the paramagnetic spin glass transition. A characteristic temperatures features was a considerable shift of the transition temperature to freezing 11-12 Kelvin for the nanoparticles, compared with the bulk crystals equal 5-6 Kelvin. Similar increase of the freezing observed also in investigation magnetic susceptibility for CD mangan S nanoparticles. And conclusion with our results. And thank you very much for your attention.
So thank you for your report. Please question.
You use magnetic ablation method for production of nanoparticles. How can you change the content of manganese? You said that properties depend on the content of manganese using this method.
Please repeat questions. Maybe close the microphone.
You use magnetic ablation method for preparation nanoparticles. Is it possible?
We don't apply magnetic field for preparation nanoparticles. We obtain nanoparticles by using pulsed ablation in liquids. And also when we study optical properties of optical, we apply magnetic fields. I know what your question, because it's different. If we apply magnetic fields when we obtain it, it's as a result in time.
So we don't have more time for questions. Thank you again for report. And the next speaker, this one, Anna Pagios-Vergi from Jersey Harbor Institute of Catalysis and Surface Chemistry, with report application of nanocomposite metallic ink for fabrication of conductive coatings at low temperature sintering. This presentation online, so please.
Good afternoon. Do you hear me?
Yes, we can hear you.
Great. Do you see my presentation?
Yes.
Yeah, that's good. Please press F5 for full screen.
Yeah, now it's okay?
Yeah, that's good.
Okay, perfect. So, good afternoon. Thank you very much for a nice introduction. I would like only to add that it's for me a great pleasure that I can present our results regarding application of metallic ink based on nanoparticles for fabrication of conductive coatings at low temperature sintering. At the beginning, I would like to tell you what was the motivation of our research. So among metals, silver has been the most commonly used so far as component of conductive materials. Although silver has obvious advantages such as high conductivity and stability against oxidation process, it is too expensive for large-scale commercial application. One of the candidates which can replace this costly silver is nickel, because it has still quite good conductivity, while its price is much lower than silver. Therefore, our first motivation was to use nickel nanoparticles for the fabrication of low-cost conductive materials. Our next motivation was the growing interest in the application of conductive materials based on metallic nanoparticles for the fabrication of printed electronic circuits on flexible substrate as a way to the production of different kind of flexible devices, sensors, and other types of materials. Let's now look at the objective of our research. So it was obtaining a new product in the form of inks or paste based on metallic nanoparticles, especially nickel silver with core shell structure, which will be used for the fabrication of conductive coatings or patterns at low sintering temperature. Before I will present the obtained results, I would like to tell you why we would like to use monometallic and bimetallic nanoparticles for the preparation of conductive materials. Because firstly, by using nanoparticles, we can lower the temperature of the fabrication process of conductive materials, because metallic metals in nano size have much lower melting point than their form in the macro size. Also, by using core shell nanoparticles, we can protect nickel nanoparticles as the core of this structure from the oxidation process by the presence of the shell on their surface. And finally, we can improve the conductivity of nickel by the presence of this silver shell. The mentioned before, the main aim of our research, we obtained by the implementation of the individual research stages. First of it was the optimization of the synthesis process of two types of metallic nanoparticles. They were core shell nickel silver nanoparticles and silver nanoparticles. I will not present in details the process of the synthesis because the time of the presentation is limited, but if you are interested in it, you can find it in our published papers. So those synthesized nanoparticles we used for the preparation of inks, which were based mainly on the nickel silver core shell nanoparticles and doped with a small concentration of silver nanoparticles, which is important from the economic point of view. And then those inks we coated on the glass substrate by using bar coating, and then the thermal sintering process was performed, which is usually required because of the presence of polymeric stabilizers, which cause that the resistivity is usually too high to be practical of importance. And after that, we characterized the properties of sintered coating. We synthesized silver nanoparticles with the size about of 30 nanometers and with the spherical shape. The core shell nanoparticles were characterized by the size of about 220 nanometers, and also they were almost spherical, as you can see in the presented CAM and PAM images. Then we analyzed the chemical composition of the dispersion of nickel-silver core shell nanoparticles. We were especially focused on the atomic percentage of metallic nickel and nickel oxides regarding the stability of nickel nanoparticles against oxidation process. And as you can notice in the presented spectra A, the atomic percentage of metallic nickel was very high. It was almost 90%, which means that this silver shell provides good protection of nickel from the oxidation. Also, the atomic percentage of metallic silver, as you can see in the next spectrum, was really high, which provides this good protection for the nickel from the oxidation. Then we prepared the inks based on those two types of metallic nanoparticles, and we had to optimize the properties of such ink to obtain the coatings with high quality. And we optimized the wetting properties of this ink by using as wetting agent commercial surphenol. And we found out that the most uniform coating we obtained for the concentration of it 0.05%. And this type of ink we selected for the next experiment. It was the sintering process, and we analyzed the dependence of conductivity of coatings on the concentration of silver nanoparticles, as well as on the temperature of sintering. And as you can see in the presented graph, the conductivity of such coatings doped with the silver nanoparticles at all ranges of applet concentrations were much higher at all ranges of temperature of sintering in comparison to the ones without silver nanoparticles. It could be related to the good conductivity of silver, as well as that these smaller silver nanoparticles created some kind of the nexus between these bigger core shell nanoparticles, which improve their melting. But the most promising results we obtained after the sintering process at 150 degrees when we use the concentration of silver 1%. These results are promising for the application of such coatings for the fabrication of the flexible patterns. And other type which was sintered at higher temperature, but in this case we use the lower concentration of silver nanoparticles, is promising for the using for larger industrial application because of this economic point of view. And the conductivity of such coatings was about 35% of that for bulk nickel. Then we analyzed the morphology of the coatings doped with optimal concentration of silver nanoparticles. As I told you before, it was 0.5% and 1%. And we studied it after the drying process, as you can see in the images A and B. And after the sintering, it is presented in the images C and D. And we observed that after the sintering process at optimal conditions, the nanoparticles were well merged, and they created almost uniform structures, which also provides, I would like to say that we prepared the nanometallic ink we use for the fabrication of conductive coatings, and we obtained the promising results for the coatings doped with low concentration of silver nanoparticles. It can be used for the fabrication of conductive materials at larger industrial scale. And another type of coatings which we obtained at low temperature sintering can be used for the preparation of the conductive printed patterns on flexible substrates. And in the end,
thank you for your report. And please, questions. Yeah, one question.
Thank you for your talk. You have said that you used silver to protect nickel nanoparticle from oxidation. And what agent do you usually use to protect silver from oxidation?
What agent? Could you repeat, because the quality of voice online is really bad.
Repeat questions, please.
Okay.
More loud.
Yes, please.
What chemicals do you use to protect silver from oxidation? It is yellow in
I listen question.
What chemicals?
Yeah,
yes.
During synthesis, what chemical used for protection of oxidation for silver?
Okay. For silver, it was used the sugar maltodextrin for the silver nanoparticles. It was the stabilizing agent.
Yes, thank you. Thank you for your answer. One more question? Yeah, please. One moment.
Okay. Thank you for your report. It was very interesting. So I have several questions. First, you told that, the first slide, you told that your materials can be used as conductive materials. You show aluminum and copper and your material after that. So my question is the next. Is it possible to use your material in electrochemistry as the foil for disperse some electrode materials on the surface of your material? So, is it possible? Because it's known that for some, for example, anode materials, we use usually we use the copper foil, and cathode materials we use the aluminum foil. So, is it possible to use your materials in electrochemistry?
You mean if it is possible to use nickel nanoparticles in what kind of materials? Because again, I heard only the part of the questions, so I am not sure if I could understood it.
Okay, I will try to repeat short. So you told about your alloys, nickelum and silver together. So the question is it possible to use your materials as a foil for some electrodes, for example? Did you interested in this question?
Yes, I think that it is possible to use it, but the field of my research is based mainly on the using of this kind of materials for the fabrication of the electronic patterns. But yes, I think that it's also the good idea for the application.
Okay, thank you very much. In the next question, maybe it's not question, it's maybe I can't understand clearly. So you told that you used nanoparticles, but when you show your results, you show that your particles have the size 200, approximately 200 micrometers. So the question is the next. What size of the crystal size you have in your samples? Because as I understood, you show the particles, but it's known that the particle consists from the small crystals.
Yeah, you are right. The nickel silver crystal nanoparticles had the size about 200 nanometers. But in any case, in this case, we paid attention mainly on the conductive properties. So for this size, the conductivity was okay, was high. And also the most important for us was to obtain the nanoparticles not bigger than about 400 nanometers. Because this kind of ink we would like also to use for the preparation of patterns by using inkjet printing method. And in this method, it is important to not block the head office. And when the nanoparticles are smaller than 400 nanometers, it is okay. So for us, this size is fine, but of course, it would be better to obtain smaller nanoparticles. But to prepare it, we need to consume more energy, more reagents, and it is also not good from the economic point of view.
Okay, thank you very much. I see. So thank you for your report.
So again, thank you for your report. Thank you for questions and discussion. So next speaker, Yulia Bonder, Professor Yulia Bonder from State Institute, the Institute of Environment Geochemistry of National Academy of Science of Ukraine, with report fabrication of nanocomposite polymer granules for enhanced removal of cesium radionuclides. Please. I do not know where. Once a moment. Юлия Бондарь.
Yes.
So, you reading? So, please.
Operation of nuclear power plants and nuclear facilities are accompanied by formation of large volumes of liquid radioactive waste, as well as increase of radionuclides to the environment. For this reason, the development of integrated approaches to the radioactive waste management should include decontamination of liquid radioactive waste through selective removal of radionuclides. The cesium radionuclides that escape into the environment are a serious threat to the human health. That is why the serious attention has been paid to the methods of selective removal of cesium radionuclides from contaminated waters. Dozens of different organic and inorganic adsorbents have been synthesized for selective removal of cesium ions, but only a few groups have shown stable selectivity in high salt solutions. Among them, the adsorbents based on insoluble double ferrocyanides. However, ferrocyanides are usually synthesized as fine or ultrafine particles that cannot be employed directly for separation radionuclides. The last achievements in nanotechnology allow to develop two approaches to synthesis of nanocomposite adsorbents. The first approach includes the incorporation of preliminary synthesized nanoparticles into the pores, voids, or channels of solid matrix. The second approach includes the in situ formation of inorganic nanoparticles onto the surface or inside of solid supporting matrix. As a supported matrix, porous silica gel, clays, xylides, metal oxides, or macroporous polymer granules can be used. Our approach includes, from economical points, the combination of macroporous polymer granules with ferrocyanide nanoparticles can give us the good adsorbents with high selectivity for separation cesium ions. We used macroporous cation exchange resin with sulfonic acid groups because it is a commercial product of large-scale market, because it's rather cheap, and mobile macroporous polymer net is an ideal matrix for forming a fixation of various inorganic nanoparticles inside the granules. So in this slide you can see why we used polymer ion exchange granules and insoluble double ferrocyanide, the advantages and drawbacks. The advantages of polymer granules: cheap commercial product, wide working pH range, low cost, and wide using in nuclear industry. And drawbacks: low selectivity to cesium ions. Advantages of ferrocyanides: high selectivity to cesium ions, but drawbacks low mechanical stability. So our decision to obtain an ideal adsorbent for cesium radionuclides, the incorporation of insoluble ferrocyanides inside the pores of polymer granules give us good solution. On this slide you can see why we choose such way, because a lot of active sites on the surface of nanoparticles and multi-scale transport and multi-scale adsorption when we used composite granules. So on this slide you can see our approach. Our approach includes in situ synthesis of potassium copper ferrocyanide nanoparticles inside the commercially available polymer granules with charged sulfonic acid groups. Our hypothesis that synthesis of composite adsorbent proceeds as a result of precipitation of ferrocyanide nanoparticles inside the pores of polymer granule due to the full reactions, and we used porous structure and charge groups as nanoreactors for the formation and fixation nanoparticles. On this slide you can see the images of original polymer granules. They have cream color and smooth surface, and after after synthesis the composite polymer granule change color to dark brown, and the surface become more rough. The microanalysis results show the elements of potassium copper ferrocyanide, and also the XRD analysis confirms the formation of ferrocyanide fuzz on the surface and inside of polymer granules. The synthesized polymer granules we tested for selective removal of cesium radionuclide. High selectivity is the key parameter of any adsorbent, since the radionuclides are present in trace amount in complex solution with high content of inactive and competitive ions. Sodium ions are abundant in both fresh water and seawater, as well as they are the main chemical component of typical evaporated concentrate from nuclear power plants. That is why we tested our polymer granules and composite polymer granules in a monocomponent and multi-component solution with high sodium content. One can see that granules, original polymer granules and composite polymer granules demonstrate high adsorption efficiency in when adsorption occurs from monocomponent solution. When adsorption occurs in a multi-component solution with high sodium ion content, the polymer granules demonstrate adsorption efficiency about 0, but composite polymer granules demonstrate a rather high adsorption efficiency even when the sodium ions content is about 1 mole per liter. Also, composite polymer granules demonstrate high adsorption capacity and working ability and wide pH range from 2 till 9. That is why the synthesized composite polymer granules with potassium copper ferrocyanide phase are characterized by high selectivity to cesium ions in the presence of large excess of competing sodium ions. So the conclusion that nanocomposite materials was synthesized, same in XRD technique confirms the formation of ferrocyanide phase. Composite granule are characterized by high adsorption capacity, and they characterized a high selectivity to cesium ions in the presence of a large excess of competing sodium ions. The composite polymer granules can be recommended for the selective removal of cesium radionuclides from natural and industrial wastewaters, as well for purification of low-level liquid radioactive waste with the high concentration of competing sodium ions.
So thank you for your report. Please, questions? Please. Микрофон. 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 Где микрофон?
So, as I understood, you use the commercial polymer for your test. So, what the information about this polymer can you present? I mean that what's the functional groups there was inside your polymers. So, if they influenced on the properties of your components inside. So maybe there was the interaction between, or not.
With commercially available polymer resin with sulfonic acid groups, these resins widely used in nuclear industry. That is why we use only this resin. Of course, the charge groups influence on the stabilization and fixation nanoparticles inside the polymer granules, because we tested these granules during 2 weeks in strong acid and strong base solution. No release of nanoparticles inside the polymer granule.
Okay, so not interaction between them.
So thank you for questions, and thank you for report. And next speaker, Susanna Lavare from University of Warsaw with a report from Khalid Perovsky to anisotropic semiconductors, new method of cadmium sulfur nanorod synthesis. So please.
Good afternoon, my name is Susanna Lavera. I'm from University of Warsaw, and today I want to tell you about the project that was part of my master thesis research, a new synthesis method for rod-like cadmium sulfide. At the beginning, I will say a few words about the perovskite and crucial nanocrystals, because this new synthesis method starts with perovskite synthesis. I will introduce you to the synthesis method and explain how small changes in the parameters of the reaction leads us to anisotropic quantum dots. I will show you helical structures that I've obtained with these anisotropic nanocrystals, and I will summarize and tell you about the future plans. So let's start with the perovskite nanocrystals. Lead halide perovskite nanocrystals crystallize in a typical ABX3 type of lattice, where A is an organic cation or cesium, B is a lead atom and X is one or more of the halides. In my case, we use cesium, lead, and bromide atoms in the lattice. Perovskite quantum dots have many potential applications due to their unique properties, optical properties, such as size-dependent emission wavelength, narrow emission spectrum, and high luminescence efficiency. Unfortunately, they are quite unstable especially with the polar solvents. And toxicity of lead is quite problematic if we speak about device fabrication and deployment. So great efforts were made to stabilize the structures. Among many core shell structures are the most effective and very, very useful way to control the stability. So the sensitive core is covered by shell material, especially covering CSPBBR3 with cadmium sulfide is very effective. The stability is enhanced even with the humidity of 75%. It still has narrow emission spectrum and high photoluminescence quantum yield is maintained with this structure. So cadmium sulfide is quite a good material for this kind of perovskite. That was reported in the paper published last year, and I'm mentioning it here because that was the starting point for my project. So the synthesis have three main steps. In first step, we prepare cesium and cadmium oleates. In step 2, the PbPr2 solution is prepared simultaneously with cadmium sulfide precursor. And when we add cesium oleate to PbPr2 solution, we obtain perovskites. In step 3, cadmium sulfide precursor is injected into the perovskite solution, drop by drop over 15 minutes, and core shell structures are obtained. So as you could see, after the first stage, we obtain perovskites. After second stage, we obtain core shell nanocrystals. But what will happen if we raise the temperature up to 170 degrees Celsius and prolong the reaction time? It was reported that with the longer reaction time, nanocrystals aren't growing anymore. The size is relatively the same. What happens is that shell atoms replace the core. So after some time, core will be entirely etched. And that's what happens if we raise the temperature up to 170 Celsius and prolong the reaction time, we obtain anisotropic quantum dots. So as you can see on the TEM image on the left, they are anisotropic, rod-like shape. They are around 11 nanometers long and 5 nanometers wide, which gives aspect ratio 2.5. The sample was measured on the high-resolution TEM with EDS analysis, and as you can see, or you can't, but it's supposed to be, cadmium and sulfide are the main atoms in the crystals, with small doping of cesium, lead, and bromide atoms. I've performed spectroscopy measurements. As you can see, the absorption range is quite wide, with an intensification in 437 nanometers. Emission maximum is for 672. The difference is quite large, but it may be because the impurities in the crystals, and by impurities I mean the perovskite core atoms. On the right side of the slide, you can see anisotropic fluorescence measurements. Two polarization of electromagnetic wavelength were measured and plotted here. As you can see, maximum of the emission is shifted to the right by 11 nanometers, and they differ in intensities by 0.35 after the normalization of the signal. And that's the proof that nanocrystals are indeed anisotropic. To examine what changes in the parameters cause or lead us to anisotropic quantum dots, I've performed a synthesis with 13 different fractions. First 12 fractions differs only in the time of the reaction, but 13th has a longer time of the reaction and higher temperature of the reaction. So first 12 fractions don't differ that much. As you can see, fraction 2 is quasi-spherical with the diameter around 4 nanometers. Fraction 6 is slightly bigger, still quite spherical, and the diameter is around 6 nanometers. Fraction 12 is larger. It has 8 nanometers diameter. we can say that it's slightly elliptical, but it's not anisotropic as we expected, as anisotropic as we expected. Yes. The spectroscopy measurements correlate with the TEM image. We can see that maximum of absorption and emission is shifting to the longer wavelengths when the crystal is getting bigger. A different case is for fraction 13th. It has the longest reaction time, but also the temperature of the reaction is higher. And you can see that we obtained anisotropic nanocrystals. They are very small, have 10 nanometers length, but they do have rod-like shape. And spectroscopic measurements correlate with the sample that I've shown you before. Obtaining helical structures raised a lot of interest in recent years, especially obtaining an helical assembly of nanoparticles that combines helical topology with unique nanocrystals. With unique nanocrystal properties is very interesting. We can obtain that by mixing nanoparticles covered in oleoamine with liquid crystal matrix. And with proper crystallization conditions, we can obtain helical assembly, as you can see here. What's important is that we need to control few parameters. Very important is, nanocrystal concentration, liquid crystal matrix concentration, and heating and cooling rates during the crystallization process. Here you can see again helical structures on TEM image, and on the right side of the slide you can see images from polarized optical microscope. They were made for two orientations of polarizers. As you can see, when we change the angle between the polarizers, the domains stay the same, but the color changes. It's that right-handed and left-handed helices create separate domains. So as you can see here, the domains stay the same, but the color changes when we change the angle of the polarizers. That means that indeed this liquid crystal matrix creates helical assembly. So for the summary, during one synthesis, I'm able to obtain three types of nanocrystals: perovskites, core shells, and anisotropic cadmium sulfide nanocrystals. This is a new approach for cadmium sulfide synthesis, and I'm able to obtain nanocrystals in aspect ratio 2.5. I performed full physical-chemical characteristic of these samples and stability tests for them. I was able to obtain a helical assembly of those rod-like nanocrystals. In the future, we're going to measure optical properties of these helical structures. That's everything from me today. Thank you very much.
Thank you for your report. Very interesting. So, please, question. Please.
Thank you very much for your report. So I have a question. You told about the three types of the materials. So the question is about the material core shell, with the structure of core shell. Did you realize the comparison between these materials with another? Because why I ask you? Because the core shell structure is very famous for in different spheres of the research, for example, in electrode materials for creation new electrode materials. So did you have any advantages of these materials in comparison with others? Please, if you have this information.
Perovskites or
yes, perovskites, yes.
Well, the main one is the stability. They are much more stable. I didn't show the results here, but I did perform the stability tests, and perovskites are not stable under conditions like we have outside. Core shells are much more stable. They passed the test, so after a month they were still the same without any big changes in the tests.
Okay, thank you very much.
I actually have two short questions. First, for which application you use your perovskite system? It's probably for lead-emitting diodes.
Yeah, usually yes. I'm not going further with this research.
Okay. So and another question. So you demonstrated that if you fabricate this core shell structure, so you improve stability. We have an idea about the mechanism. So does it mean that you passivate a surface of your nanocrystals, and then you have a smaller number of traps? Or do you have any idea why it became more stable?
It's because perovskite lattice is very, very sensitive to
it's known,
solvents,
yes.
right? Because it's ion. And when we cover it, the humidity in the air is perovskite.
Okay, so you simply prevents physically
Yes.
contact of the
Yes.
vapor and the perovskite.
So thank you again for report. And now time of the lunch. We continue our conference after 2 o'clock. So thank you again.
So, dear participants, we continue, and the next reporter is Dr. Andrei Kadachnyuk from the Institute of Physics of National Academy of Science of Ukraine. So, please.
Good afternoon, everyone. My name is Andrei Kadachnyuk. I'm from Institute of Physics, and today I'm going to talk about density of states distribution determination in organic semiconductors using experimental technique and advanced computer simulation. First of all, I would like to thank organizer for last-minute inclusion my talk into the conference program. This work is a collaborative work between Max Planck Institute in Mainz, Institute of Physics in Kiev, and the Merck company from Darmstadt. And I have quite limited time, and I'm just going to give you a flavor of our most recent review paper published in Chemical Physics Review, where we actually applied different method to characterize organic semiconductors. Actually, the major application of organic semiconductors is organic light-emitting diodes. Nowadays, it's a huge industry. So you see that in next year, it will be more than $48 billion. And nowadays, a lot of different products is realized, OLED TV, smartphones, also flexible displays, and also lighting. And all these displays are made of OLED pixels, which consist of organic molecules. And one problem is how to find right molecules for improved OLED devices, because there are millions of molecules, and it takes enormous time to characterize molecules and to find out if it's suitable or not for real practical application. So one idea is that we can save the time, because it normally takes several years to characterize completely experimentally one molecules. To save the time, we can use so-called in silico approach. In silico, it's a pseudo-Latin word, which means that calculations are done or simulation are done by computer. Silicon, it's a synonym of computer processors. And if we would be able to predict theoretically physical properties of molecules, then it suggests very attractive perspective that actually we can design a molecule at the very beginning with the desired properties. So for that principle of such kind of simulations, that ground state geometry and could be done using the first principle calculations. Then we used molecular dynamics simulation in order to simulate amorphous morphology, because all organic semiconductor films are amorphous films, and you have to somehow mimic this amorphous structure. And then if you have actually a film, so it's already macroscopical object, we can apply, for example, kinetic Monte Carlo simulations to determine mobility. Mobility is a key parameter for all its devices application, because it's determined electroconductivity of organic films. in order to check and in order to verify this approach, we, as I said, we applied experimental measurements and advanced computer simulation. So we have chosen these 12 organic molecules, which are very typical model system used for as a OLED host in practical applications. So they are, all of them are known, and we actually theoretically calculated several characteristics of these molecules, and also we studied some of these perimeters using our technique, thermostimulated luminescence. And as I said, organic semiconductors are amorphous films, and this to explain you what is the meaning of energetical disorder. If we have a molecular crystal, then we have just a well-defined conduction level and valence level for transport of electrons and holes respectively. But as soon as we have a disordered system, positional energetical disorder results in the information of density of state distribution. So instead of narrow level, we have a typically Gaussian distribution with a width of sigma. And this perimeter sigma is called as an energy disorder perimeter. This is a key perimeter because, as you can see from this relation, it determines the mobility. Mobility depends exponentially upon the width of the density of state distribution. So, and in my talk, I will focus just on this perimeter, width of the density of state distribution. Experimental determination of this perimeter is not a trivial task, and can be done with a range of technique. This technique were used before in literature with a different degree of success. And our technique is a thermal stimulated luminescence, which we suggested some time ago, and it's a unique technique which could be applied to a strongly disordered system. So just a few words how it works. So we assume that we have a Gaussian density distribution, you see here. And if we generate charge carriers with light excitation at liquid helium temperature, then carriers try to relax towards tail states of the density state distribution. So as schematically shown here. So, and they form so-called occupational density distribution. And then when we start hitting our sample, carriers can thermally release from deep tail states of the Gaussian density distribution, and they recombine and they produce light. And this light intensity versus temperature is called thermostimulated luminescence. We did some Monte Carlo simulation to prove that this is a correct picture, that indeed if we have Gaussian dose distribution, then occupied dose distribution should also be of Gaussian shape. And if we analyze this shape, we can reconstruct the width of the dose distribution. This is how we do this. Just one example. We use cyan, MCBP cyan, and we measure first TSL curve. Then we apply so-called fractional glow technique to measure so-called effective activation energy, and then we can replot these curves in Gaussian representation, and from the slope of that plot we can determine the width of the dose distribution. So, and as you can see, it's a perfect Gaussian plot, so which over 3 orders of magnitude demonstrate Gaussian shape. This is examples of our TSL measurements we applied for different OLED hosts. So here you can see TSL curves, and here a Gaussian analysis, and from the slope of this analysis we can determine the width of the dose distribution. And as you can see, it increases for the approximately for the material with sigma of 88 millieV to more than 150 millieV. The same perimeters could be calculated using molecular dynamic simulation, which I mentioned you. So starting from the first principle calculation, then amorphous morphology was formed. For that, molecules were heated up to 300, 500 Celsius, and then quenched quickly within several nanoseconds to room temperature in order to freeze down amorphous morphology. And then using quantum mechanical calculation, dimensional functional theory, position of LUMO and HOMO levels were determined, and also the spread of these HOMO-LUMO levels. And this allows to obtain this Gaussian density distribution, which was simulated for these molecules. So this probably I will skip. And this is a final result. So this Gaussian dose distribution was determined for all 12 molecules, and you can see that they are quite different. In this slide, you can see a correlation between experimentally measured values and the width of the dose calculated with molecular dynamics. And the correlation is quite well for this material, which actually validate this theoretical method of the calculation of material perimeters, starting from, as I said, from quantum mechanical point of view. I will skip this. What next? Actually, applying DFT theory, we can calculate also reorganization energy and transfer integral. Because the jump rate is determined by the Marcus theory, and this is the two key parameters for the charge transfer in the Marcus theory. I forgot to mention that all this theoretical work was done at Max Planck Institute in Mainz. And then, finally, applying kinetic Monte Carlo simulation, we can calculate charge carrier's mobility. Here you see 12 plots for the temperature dependence of the mobility, for the whole mobility in this material. And as you can see, these mobilities, they are summarized. They are changed by almost 6 orders of magnitude. And the reason for such huge change of charge carrier's mobility is the change of the energy disorder. So now I would like to finalize, to conclude my talk. So we presented experimental verification of the suggested in silico simulation method. So, and we demonstrated the energetical disorder has the greatest impact on the charge carrier's mobility. So, and here you can see our recent publication where you can find all the details of this work. Thank you for your attention.
Okay, so if somebody have a questions, please ask.
Could you please open slide number 13? Oh, yes. My question is what specific programs of molecular dynamics and electronic structure do you use in this modeling?
Actually, our group was responsible for experimental studies. Okay. Actually, so it's a bunch of novel theoretical methods were used, so I simply don't remember all of them. Okay. So as you can see, 3,000 molecules were simulated, and so if you can go to our publication, it's open access. So, and you can find all the details of that. So I must say that the theoretical group of my Max Planck Institute is led by our former PhD student, Denis Andrienko, who is the head of the theoretical group, and he probably is the most, how to say, advanced expert in such kind of simulation, I would say.
Okay, thank you.
Maybe somebody else? Okay, so I have a question. You told about the organic materials for your research. So the question is the next. So you used the molecular dynamic simulation, and it's interesting for me. Did you fix the bonds, the special bonds in organic molecules using your methods? So I ask you about the chemical background of your research, if you have. Thank you.
Okay, so as I mentioned, first of all, as a ground state was calculated using first principle calculations. So this gives you a structure of the molecule. But then, as I also told, that molecules were heated up to several hundred Celsius degree. And these molecules are very flexible. As you can see, there is a dihedral angle, and they can have different conformations. So, but then molecules were quenched very quickly to the room temperature, and it's assumed that all conformations are fixed. And we really observe that it's really the case, that it's not just amorphous structure of molecular positions, but it's also amorphization due to the different molecular conformations. So chemical formula is there, but I mean they could be in different conformations. But then the most tough task is to calculate force field. So for the force field, and this was the aim of this work, to make a molecular library. So to calculate force field and all perimeters which can be used by others to extend this molecular library for pre-screening of organic semiconductors for practical applications. That's an idea, actually.
Okay, thank you. So.
Okay, thank you.
So the next reporter is student Mateusz Pawlak. Please.
Okay. Which one is yours? Here, yeah.
Good afternoon. My name is Mateusz Pawlak, and I am member of Wiktor Lewandowski's research group at Faculty of Chemistry at University of Warsaw. And in my presentation, I'm going to tell you about a surprising observation that we have made with Maciek Bagiński during our research on helical structures, which you can see on the right-hand side. To begin, let me start with the idea of formation, this kind of materials. Such helically oriented nanoparticles can be formed using approach which was described in by our group about 2 years ago. This material is composed of two types of two components. The first component is organic compound, which you can see here, and I will call it dimer because it is composed of two identical branches, arms, which are connected to each other by alkyl linker. And the second component of this material are, of course, nanoparticles. But to ensure good miscibility of nanoparticles with dimer, these nanoparticles were covered with organic ligand, which structure is similar to structure of this dimer. So this arm of dimer and this terminal chain of ligand have the same structure. And if we melt pure organic dimer into isotropic phase, then after cooling it forms layered crystals, what is typical for such kind of molecules. But also small amount of helical structures is formed. But if we introduce to this molten dimer nanoparticles, then after cooling, different kind of structure is formed. Then helical structures are formed, and in core of these helices, dimer molecules are situated, and these twisted ribbons made of dimer on the edges have nanoparticles oriented into such helical structure. And the question which I wanted to answer was how length of the central linker in organic dimer influences on formation of helical structures. And to reach this goal, in first step, we had to synthesize series of dimers with different length of this central alkyl chains. We did it in Mitsunobu reaction between precursor, which we synthesized before, and diols with different number of carbon atoms. And in such a way, we synthesized a series of 9 dimers with different lengths of central linker. And what we observed is the fact that really formation of helical nanofilaments is strongly dependent on length of this central linker. Because, for example, when we compare result for dimer with 7 carbon atoms in linker and 8 carbon atoms in linker, we can see that helical structures are formed only by dimer with 8 carbon atoms in central part. But going further with this analysis, we also can say that similar comparison we can do with dimers with 9 and 10 carbon atoms in central linker. And after analysis of all our materials and all our dimers, we can conclude that nanoparticles induce this formation of helical nanostructures only if dimer have even number of carbon atoms. And this result is surprising because such helical structures, helical nanofilaments, is a structure which is quite good, quite well known in liquid crystals. It is known for about 30 years, but let me describe you the mechanism of formation of such helical nanofilaments. When molecule has a bent shape, then when it forms a smectic phase, so a layered structure, then this layer is tensed because there is a mismatch between upper and lower surface of this layer. And this tension leads to saddle splay of the layer and finally formation of a helical nanofilament. But, we can say that this mechanism is similar to the reason why potato chips after frying have curved shape, because when we fry flat potato chips, then temperatures of upper and lower surface of chips are not exactly the same, and this difference between temperatures leads to the fact that tension appears and we obtain curved chips. But from this reasoning, conclusion is that dimers with odd number of carbon atoms should form such helical nanofilaments, because these dimers have bent shape like this on this scheme. But what we observe is a completely opposite effect. We observe that helices are formed by molecules with even number of carbon atoms, so molecules which have a rather linear shape than bent. And to answer this question, we are performing more detailed measurements. For example, we performed X-ray diffraction and polarization microscopy measurements, which led us to answer the question, what are phase sequences of this dimer? And looking on this table, you can see that these phase sequences are similar for all of these dimers, because we have at lower temperature crystalline phases, and before melting to isotropic phase, one liquid crystalline phase is formed, phase called smectic C, so layered structure. And on the left-hand side, you can see one of XRD patterns. This is for dimer with 10 carbon atoms in central linker. And you can see exactly what we concluded from this phase sequence, because we have at lower temperatures, these three plots, we have sharp peaks both at smaller angles and at higher and at wider angles. But at higher temperature, where we have smectic phase, then we have sharp peak only at smaller angles, but there is also some kind of disorder in this phase. So at wider angles, we see broad signal. And the second interesting thing that we saw is the fact that looking on the polarization microscopy images of our phase at low temperature, we observed that images for even dimmer are much darker. And polarization microscopy is a technique which tells us about birefringence of material which we are observing. So what we can say is the fact that at low temperature, this phase formed by even dimmers has much decreased birefringence. That is why I called these phases as LB, low birefringent. And this decreased birefringence is a good sign, because it says that molecules in this phase are not oriented parallelly into the same direction, but these molecules orientation of molecules changes with position. So like, for example, on helix, when we are moving on helix, then orientation of molecule changes. And we also cooperate with Professor Guillermo González Rubio from Madrid, and his group is performing molecular modeling calculations, and their results also show that these molecules have a tendency to form layered structures. And what also is interesting, you can see that these layers, this is results of this simulation, are not flat, but they show some kind of curvature. So for larger layers, maybe they really want to twist into helical nanofilament, and it is also seen in theoretical calculations. And these are results which we obtained up to now, and the next plan is to fabricate monocrystal of dimmer and perform XRD measurements, which will allow us to answer the question how exactly molecules are oriented in phase, in this low birefringence phase. And we hope that all our results will let us answer the question why we are observing so unusual and opposite of even effect in our samples. And also answer the question which we are looking for about 2 years: what is the role of nanoparticles in formation of these helical structures? Thank you very much.
Okay, so any questions, please?
Thank you. What kind of application you suggest for such materials? In connected question, actually, have you checked the optical properties of these samples in general?
Mm-hmm. Okay, these are some first attempt. So only the fact that we obtain such structure is interesting. But in our group, we also showed that such kind of materials where nanoparticles are ordered into helical structures are of course chiral, and they have chiral properties. So all the photonics, so all the photonic applications may be here possible. And also a colleague from our group, Dorota Grzelak, also will tell more about these applications.
Thanks, it's really interesting. It's actually no question, but I have some comment maybe helping here. You're changing from even number to odd number, and I saw in your molecules you have a carbonyl group. Maybe you can think about dimer by using what we call it hydrogen bond or kind of, and this making some kind of dimer, and through stress inside the molecules you can have this helical. And if it started at the beginning, it would be actually running
yes,
this way.
it can be possible. Thank you.
Okay, so thank you very much.
Thank you.
Yes. So the next reporter is Professor Dr. Amir Fahmi, please.
Thanks a lot for many people coming. First of all, I'd like to thank the organizer for letting us presenting some of our results. And I'm sorry my lecture after lunch, but I try to make it fast as I can. And I will speak quite considering after lunchtime. Okay, before I start, I like just like that, to attract your attention about hybrid material and how nature can design well-defined structure of hybrid material, have 2 or 3D structure, have porous-like structure, and I was really fascinated with this kind of 1D structure and how it works. This is a group from Eisenberg groups. I visited her group in US. It was quite interesting. After that, there are many groups start to make this inspirations from different kind of organic molecules. Even group from Japan, they managed to put different kind of inorganic magnetic nanoparticle in this well-defined structure. And my colleague, Professor Axel Müller from Bayreuth, actually managed to make a very interesting kind of polymer and kind of a hybrid material. I recognize hybrid material is quite interesting. This is very common to use right now. And for this reason, I focus my talk about hybrid material and nanostructured, how to fabricate hybrid material, but I will work more likely in 1D structure. That's my name, and my university is somewhere here between Germany and Holland. By means, if you visit my group, I promise a nice German beer and a nice cheese from Holland. That was a simple introduction. I will speak a little bit about nanofabrication. More likely, I will put more emphasis on self-assembly. I try to give you approach about how to control structure, organic, inorganic. I put with me here 2 models how to use self-assembly to structure 1D structure in organic molecules, dendrimers. And for biological people, I like to show a little bit about elastin-like polymer. At the end, I will give you approach about making 1D structure, but uncontinuously by using what we call it electrospinning methods. Before I start, I like to give you a little bit approach about self-assembly. And in self-assembly, it is actually a spontaneously kind of process, working mainly in minimize the free energy. I think all of you know that. And we do have 2 types of self-assembly. You have static, we have dynamic. In principle, this is our dream of every material scientist. Just put molecules together, adjust them, and then you have a cup of tea, you come back, you have a nice structure like that. And this is actually working very perfect, controlled by using thermodynamics. In principle, we have 3 different types of self-assembly. You have co-assembly, just mixing 2 buildings blocked together, you make the structure like that. Or we have directed self-assembly, which I'm going to talk about it today. You're having one driving force. It should be actually following this kind of structure. And we have what we call hierarchical self-assembly. By means you have 2 buildings block, you put it together, you're making structure, and this structure, it works as a buildings block to another structure, and so on. This is more likely using this in biology, and it's well-defined kind of structure. But if you're getting in complex structure, you do need to have a complex mechanism going in. Let me introduce my concept. I bring 2 worlds together, organic and inorganic. From the inorganic, you have very nice functions. You improve the mechanical properties, optical properties, magnetization. The inorganic more likely giving, or the organic giving the flexibility, self-assembly and processing. Putting them together, functional material. If you put functional material in well-defined structure, you can facilitate multifunctional material. By means you're making one material, making different kind of functions, and this is very useful in miniaturizing
devices. Having a many type of application, medicine, you can diagnostic tools, just to mention few in energy, photovoltaic, optics, data storage, and optical code. There are many type of application we are involved in this type of applications. In my research, we're having decent track records in this kind of organic molecules, copolymer, dendrimers, biopolymers. As you see, we receive different kind of structure, 1D structure, 3D structure, 2D structure, but today I will speak more likely about 1D structure, how to make wire and different kind of 1D structure. At the beginning, as I mentioned, I like to use two important types. One is dendrimers, and dendrimers is very interesting molecules, having or molecules like trees, having a lot of branch, and having different generation, as you can see, smaller generation 0, 1, 2, 3, 4. It is not easy to make this. You need a good polymer chemist that you can have it this, but having huge number of advantage well-defined monodisperse by means, if you like to adjust the molecular weight, you say 5,420, you will have 500,420. It is very defined molecules. And what we're looking for, we're looking to template inorganic nanoparticle inside, and we're using dendrimers as a nanoreactors. By means, our aim, as our colleague mentioned today from different lectures, we like to make self-assembly. You have to have well-defined size and size distribution of your particle. For this reason, we try to use different type of inorganic. We're using here, for example, gold. We use the cavity inside these molecules that we can control the size and size distribution. Interestingly is, if you're having small generation of these dendrimers, you're having bigger size, higher generation, you have smaller size. And as you see, we have huge number of advantage, and this can facilitate what we call it well-defined structure in self-assembly. We done exactly the same. We have the dendrimers. We put the inorganic particle in. We switch the electrostatic charge inside, and we try to adjust the charge that we can have fiber-like structure, and this is based on metallic structure. In this case, we use cadmium. I will tell you why I'm using cadmium here, because we like to have a precursor for semiconductors nanoparticle, and we found it is quite easy that you can just align this cadmium wire from dendrimers. And to make it more interesting, we try to put another kind of metal that we can align gold nanoparticle along the wire of the dendritic-like structure here. As I mentioned, we use cadmium that we can have cadmium selenide. It is a very interesting kind of molecules as a marker. Nevertheless, it's pretty toxic. And this is one thing it's making it's not easy to work with. However, it have another type of application. We make this cadmium selenide in this wire-like structure, and we can see we have a very nice fluorescence here, about 570. And if we like to manage the same strategy that we can quench the fluorescence, we adding another type of metal-like structure that we can have this gold nanoparticle, and you can see gold can easily quench this fluorescence-like structure. That was the first short story. I like to go to the second story here. For biological people, we like to use what we call it elastin-like polymer. This is one of my friends actually in Spain. He told me he having a nice block of amino acids, and I told him if it will be nice if you can change one of the amino acids in between, that I can switch that charge in and can working as a driving force for self-assembly. Elastin-like polymer is a recombinant DNA technology. You can produce it. It's biocompatible for sure, and can be used as a very good candidate in self-assembly. We manage the same strategy. We're using metal, and we put the metal by using or grabbing the metal by changing the charge of one of the amino acid, and we can have this charged, or we adjust the surface chemistry of this kind of building block that we can have this kind of fiber-like structure, and then we add another kind of metal that we can have what we call it semiconductors wire-like structure. And as you can see here, through just a very simple tuning by pH, we can have pH 3, we still have aggregates-like structure. If we increasing the pH a little bit, we can have a start to form a nucleus-like structure, and here in pH almost neutral, we have 7.2, we having the fiber-like structure. We have a problem. This is a nice kind of particle having a very nice properties, optical properties, because they are semiconductors, but they are pretty toxic. And this is one of the aim that we try to use elastin-like polymer that we can cover them or coated them that we can reduce the toxicity. And this is exactly what we done. Here we having here a high luminescence, fluorescence here. You can see the transmission electron micrographs showing here how the structure looks like, and we have a very nice alignment with discrete distance between these particles. And as I mentioned, cadmium is pretty toxic, but was the aim of this study that we just like to coat this kind of very toxic nanoparticle that make it more accessible for biological reaction. In biology, you need marker that we can make and reveal different kind of biological reaction. Cadmium selenide is a very interesting candidate, nevertheless is toxic. And the aim of this that you just reduce the toxicity, that you can have this kind of structure. The last bit, we are tired to use self-assembly because this is quite, it needs more sophisticated work. And a few years ago, I started to work with electrospinning. It's very simple. Just you have syringe. Even we make one handmade in my lab. Student, postgraduate student make it. We have a syringe. We have some button here, and you have an electrode here. And you put your polymer here. You push it between two electric field, and you can have the fiber. It's very, very easy. Everyone can do it, but not home because it's high electric field. And we can have indefinite large nanofiber. We can use the membrane. Of course, as a head of the biomaterial department, we think more about adhesion of cells and biomaterial. It was quite very interesting candidate. We use a biocompatible polymer. We modified with different kind of inorganic nanoparticle. This is also biocompatible. And we make different kind of problems we have in biomaterial, for example, tumor and different kind of another type of application. We make different kind of nanofibers. As I mentioned, it's easy. You make a solution, you put in the syringe, you press the bottom, everything is done. We modified with different chemistry. Here we use silicon dioxide. We make a different strategy from it. We made the silica N or silicate N polymer outside for biological application. We can even change type of polymer. Different percent we can making even as you see here switch the hydrophilicity, and switching the hydrophilicity is quite important that you can host well-defined number of cells in cell culture. Here we're using different ratio of different polymer, and you can see how this kind of hydrophilicity can be tuned in different way. Biological properties, we work mainly in osteoblast kind of cells. We have different kind of culture times. This is about here 6 days. You can see this kind, it can work a very good scaffold for biological samples. We use not only silicon dioxide, we use titanium dioxide as well as a scaffold for different kind of biological system. What we're doing here, actually, we change the distance, the ratio, and we can, in principle, we can generate the most, what we call it, not perfect, but it's quite very good to use in biological application. Just in the next, I show you different examples that we can control the diameter of this fiber. We can control the density. Recently, we have porous-like structure, and just here, we make polymer with 2 different types of metallic oxide nanoparticle, and we can see the cells still feel quite good and still growing in different way. We have different application going on from bones and teeth, dentists, and we have quite a good application in this direction. That was the last bit I like to tell you about it, and I hope I convinced you that self-assembly is a very strong tool to make nanofabrication and electrospinning even easier, that you can having more accessibility in different kind of application. That is a very old picture during my research group in England, Nottingham, before I moved to Germany. And of course, I like to thank my group. Without them, actually, I cannot do anything, just both sitting home or sitting in the office drinking coffee. But this is a hard worker, guys. I like to thank EBSRC, this is England, from Nottingham Innovation Center. I was director there. And BMBF is German bodies for funding. And this is a very nice calendar my research group gave it to me in my birthday when actually to show and conclude different kind of structure what we done it. And at the end, I like you to thank you for your attention. Thank you.
Thank you very much. So, any questions, please?
Thank you very much for nice presentation. What do you think about perspective of functionalization of such silica fibers using partial recrystallization of surface into zeolites? It's 3 levels porosity, it's 3 level of and very high external surface.
Yes, I didn't mention that, but our aim here, we're using biological system, and in biological system you have to control the mechanical properties of this fiber. Not only that, you have to control the flexibility, and there are cells that are very delicate, and we try to add this inside just to control the what we call it collective properties or collective mechanical properties. But honestly, we didn't look exactly how this silicon dioxide or silica inside, how it looks like. We just disperse them in the polymer, and just we make the fiber for cell as a scaffold. It worked perfectly well.
Thank you.
Okay, so once more. Questions?
It was very clear.
Okay, so thank you very much.
Thanks a lot.
So the next reporter is Dr. Lyudmila Grishchuk. Please.
I'm sorry, Grishchuk.
Good afternoon. My name is Lyudmila Grishchuk. I am from Institute für Verbundwerkstoffe, Kaiserslautern, Germany, Institute for Composite Materials. Our institute has different fields of investigation, of development, but actually we are very strong in organic composite materials for automotive sector, for building sector, aeronautic, and also for medicine. I would like to say thank you very much for opportunity to present some results from our developments that will be were carried out in the frames of the European project Reinvent. We have one aim in the project development of bio-based alternative polyurethane forms for different applications, especially for automotive. Why? Why we want to have bio-based materials? Firstly, because we want to be independent from oil and gas from all suppliers. Also, we want to have raw materials every year and standing. One more motivation for us was that all interior parts in automotive sector, in automotive industry, at this moment are fully petroleum-based. That means we have de facto free field for new development and investigation. Next aim of our project was to develop bio-based forms that have more as 50% bio content. We have started to develop not only fillet forms, but also raw forms without fillers with good mechanical properties and high bio-based content. And we have started with bio-based polyols from BASF. This was bio-based branched polyether polyester polyols. Next, polyols with aromatic groups in chain. It's very nice materials from cardolite based on cashew natural liquids. And we have in consortium partners that developed new bio-based polyester polyols. Also, we have seen if we use so many bio-based things in our formulation, we must have also bio-based emulsifiers. Unfortunately, we cannot achieve good result with bio-based flame retardants. That's why we have tested classical phosphorus-containing co-reactive flame retardant petroleum-based. And for preparation of forms, always of polyurethane forms, we need also isocyanate. And in this case, we have used petroleum-based polymeric MDI. We have tested different fillers in our investigation, bio-based silica, nanocellulose, but we have also think about coffee waste. Why coffee waste? Because for creation of nanocellulose fibers, we need expensive and complicated chemical process. For extraction of biosilica from agricultural waste, also we have best of the best 10% of yield, but we also need so many energy and so many chemicals. Coffee, it's Klondike. For example, in our institute, we have with working students 120 persons. People used more as 1.5 kilogram coffee powder per day. This means we have every day new filler for creation of bio-based polyurethane forms. In this presentation, I will present only one application of soft polyurethane forms for dashboard. Normally, if we use filler, we achieve that we have improvement of mechanical properties, and in our case, we want to have increasing of bio-based content. We have started with a quick and dirty experiment. We have prepared forms with dried coffee waste from coffee kitchen. But we have so many problems. For example, we have very strong shrinkage after foam preparation up to 15% in volume. We have also tested nanoparticles of coffee we have prepared in our institute, and particles was up 100 nanometer to 250 nanometer, but in this case we have very big problem with increasing of viscosity of component A. And of course our industrial partners say, no, it's absolute no-go, we must to have system that 100% or minimum 95% full compatible with existing produced line. And we have found optimal sizing for not strong increasing of viscosity and not strong influence on forming parameters. How we have prepared filler on coffee waste from coffee waste? We have firstly we have washed fillers or with acetone or with propanol too. Next step was drying in microwave oven or in classical oven. And then we have prepared particles with 160 and 120 micrometers. In our consortium, we have also LCA people, and they ask always, Do we have cheaper process? Do we have not so strong impact on environment? And we must accept this. And of course, we have tested different ways of pretreatment of our fillers. In the case of using acetone for version, we have 2 times smaller amount of solvent. Also, what is good for acetone? Acetone formed zeotrope with water, and we can distillate again and again and use similar solvent. In the case of propanol 2, this solvent forms 3 azeotropes with water, and we cannot make good solvent for next experiment only with distillation. We need additional chemicals. Also, when we speak about drying in microwave oven or in classical oven, in the case of microwave oven, we can win in circa 120 times. We have 120 times shorter drying in comparison with classical oven. How we have prepared forms for in our investigation? We have used similar method for preparation of industrial reference, which is petroleum-based. We have used similar mixing ratio of component A, component B, and we have achieved similar forming parameters. Start time is cream time, and rise time is end of growing of forms. Maximal density, which we must to have, is 102 kilogram per cubic meter. Of course, now if we have a light car, it's better. That's why we have oriented us for this value as maximal. And compression strength at 40% deformation must be minimum 45 kilopascal. 4 must be open cells. It's one of most important requirements for forms for automotive. We have obtained open cell forms with open cell structure, but what must we check? Not only mechanical properties, not only density. We must to check also hydrophobicity. Why? Because we have bio-based polyols, we have bio-based filler, and we must to avoid fungi formation in our end product. If we have enough hydrophobic material, we can use this form without additional chemicals that have antifungi effect. Here you can see mechanical properties and density of fillet forms with filler that have a size 120 micrometers. For form preparation, we have used 4 concentration, 1, 2, 3, and 5 weight percent in polyol. Higher concentration, unfortunately, leads to increasing of viscosity and not suitability for producing this existing line. We have tested different, we have tested fillers with different pretreatment method, and what we can see? We can say that better mechanical properties observed for acetone-washed fillers. If we have acetone-washed fillers that are dried in microwave oven, we have also higher compressive strength values. And 3 most promising systems were selected by our industrial partners to test in real condition for in-field test. If we speak about system fillet with 160 micrometer particles, here we have a small difference, but also we have better mechanical properties for acetone-washed filler and for microwave dried fillers. And if we speak about propanol 2 washed filler, higher compressive strength values, are observed for oven-dried particles. In this case, our partner has selected 5 promised formulation for next investigations. Here we can compare all best formulation with 120 and 160 mu filler, and we have better mechanical properties for forms that acetone washed and microwave dried with 120 mu. But in this case, we have simultaneously increasing of density. For forms with highest amount of fillers, this means highest biocontent, higher compressive strength values observed for system that washed with propanol 2 with 120 mu and dried in classical oven. Also, our forms must be enough thermal stable. And we have tested thermal stability in air with increasing of temperature 10 grad per minute. We have tested this in Medler Toledo device. What we can see, we have achieved better properties, thermal properties, as required. We have good forms. And we have, in this case, you can see curves for all polyurethane forms that have 3% of filler. We have no influence on filler size and pretreatment weight on the thermal stability of forms. That means if we select good forms, it's not a matter how many percent of filler we have with similar thermal stability. Here in this TGA curves, you can see curves for all forms that prepared with acetone washed and microwave dried 120 mu coffee particles. Also, we have good forms, we have better values as required, and we have no influence of concentration filler thermal stability. To test hydrophobicity of our forms, we have made measurements of contact angle with according DIN norm, with water as test liquid. We have used OCA system from data physics. And here with red are presented selected forms for next investigation. What we can see here, all forms are hydrophobic. It's good. But best of the best with hydrophobicity is form which are washed with isopropanol with highest concentration of coffee particles that have size 120 mu. To summarize, in the frame of this task of the project, we have developed bio-based forms with high biocontent. We have developed fillers for increasing mechanical properties, for increasing also hydrophobicity. In the case if we have more fillers, we have high hydrophobicity. We have tested density, mechanical properties, and other important parameters for our forms. And we can say that our forms are suitable for preparation of demonstrator car in the end of our project. Also, I would like to say thank you very much for Bio-Based Industry Consortium and for Program Horizon 2020 for support with the project, and extra thank you very much for big patience for personnel from BASF, Cardolite Corporation, and Evonik for support with bio-based materials, catalysts, and additives for preparation of polyurethane foams. And thank you very much for your attention.
Thank you very much for your report. So if someone have a question, please.
Ludmila, thanks a lot. It's really interesting. I was wondering about how the coffee waste inside the polymeric matrix behave. My concern is it could be aggregated and make macrophase separation by means you have the foams in one side and they have the coffee in the other side.
We have, in this case, we have a non-reactive filler, and we are lucky because we have very good dispersibility of this filler in our component A. Of course, we have agglomerates. We cannot avoid this. But in the case of very small concentration, we have good dispersibility, and we have de facto in polymer matrix, not in a cell.
About rheological measurement, did you conduct G prime, G double prime, elastic modulus, and storage modulus, that you can see how you can withstand with mechanical reaction against any kind of dispersion?
We have proposed this for our industrial partner, but in this case, we have answered, it's not a matter. If with mini we have very good mechanical properties, we will make.
Anyway, you are in the right track, really. Biobase is the future. Thank you.
Thank you.
So thank you very much. Okay, so the next reporter is Dorota Zelak. So please.
Good afternoon, everyone. My name is Dorota Grzelak, and I came here from University of Warsaw. And I would like to talk about chirality transfer in liquid crystal and gold nanocomposites. So chirality and chiral molecules are pretty abundant in all biological systems, such as our bodies. And their handedness plays a key role in all of these biological and chemical systems. The enantiomers that are known for us can have extremely different features, such as odor, for example, lemons and oranges, but is also a key parameter when it comes to pharmaceutical drugs. Like it can be the difference between the poison and the medicine, right? That is why the chirality is one of the biggest areas of research in chemistry. So no wonder that nanomaterials that helped in recent years further so many different areas in technological advancement has found its way also to chirality research. So in the terms of plasmonic chirality, some big achievements have already been made, such as synthesis of inherently chiral nanoparticles by means of wet chemistry, or chiral 3D self-assembly of nanoparticles via peptide templates, or using a DNA origami technique. In our group, we propose a yet different approach, as also my colleague introduced on the talk earlier. It is the approach of the liquid crystal-based self-assembly of nanoparticles into a double helix structure. In the first research, we showed that the gold nanoparticles can be self-assembled into these helical structures. It was done for a 4 nanometer diameter gold nanospheres. Then in a further step, it was reproduced for a 20 nanometer diameter dodecahedral nanoparticles, for which we were able to measure its optical properties, plasmonic chirality, in the means of near-field circular dichroism. In my work, I present to you once more the liquid crystalline matrix. And the molecule that I work with as a liquid crystalline matrix is, as you can see, a chiral. It has no asymmetric carbon atoms in its build, which poses a serious problem when you consider any application for this kind of materials. So upon freezing the material and creation of the helices, the possibility of creating left-handed and right-handed helices is equal, right? So in the process of creating such a material, we actually obtain the racemic mixture of both type of helices. To resolve this problem, we introduced to the system a small amount of a chiral molecule, which is chemically compatible with the matrix compound. It will be here called as dopant S and R. And we prepared the mixtures of the matrix compound and the dopants and checked their optical properties. As for the absorbance spectra, they did not differ in any way. But when measuring the optical properties for chirality, we were able to see that the films made with each of the dopants had opposite spectra, which suggested that we were successful in obtaining an enantiomeric excess in the creation of helical nanofilaments. The next step, of course, was to add the nanoparticles to such prepared matrix. And the amount of nanoparticles was optimized towards the biggest optical response from the whole material. We tested the 8% nanoparticle mass percentage to 24% nanoparticle mass percentage in the system. And the best result was obtained for 18% nanoparticle mass percentage in the nanocomposite. And after reaching this threshold, the G factors and the optical responses on the CD spectra diminished significantly. And why was that? We performed some observations done by optical microscope, and you can see here images from an optical microscope for each of the films from 8 to 24% nanoparticles in nanocomposite. And firstly, for the 8% and 11, you can see that there's not much of a color in the nanocomposite. It increases with the nanoparticles, and it has this violetish color. It comes from the nanoparticles and their plasmons interacting with each other and coupling. Then after 18% of the nanoparticles, we start to see this reddish hue that comes into our film. And the red color, when it comes to nanoparticles, is actually quite common, but for nanoparticles that are in colloid. So the nanoparticles that are separated from each other and their plasma cannot interact with each other, right? And then after, when we go to 24% of nanoparticles, in nanocomposites, we can see only the only the reddish color of the material. And looking further into this structures, we can see that with the electron microscope, it helps us to answer what actually happens in the nanocomposite. For the 8% of nanoparticles, we can see that in the nanocomposite there are a lot of organic matter forming the helices, but not enough nanoparticles to fully develop on the helices. That's why we see some responses, helical responses, but they are quite weak. When we go to the best sample, the 18% of nanoparticles, we can see fully formed helical structures with the nanoparticles. And then we go further and we still see some helical structures, but most of the nanoparticles is on the outside and just between the organic matter, not forming any helical structures. The next step was to say what kind of percentage of the dopant used will be the best for the development of the desired handedness in the nanocomposite. And I don't know why, but actually this was supposed to be a fuller graph with around 15 graphs, but we can see only the best results. So maybe we can you can trust me that for smaller amounts of dopant, these responses were much smaller. And then also similarly to the nanoparticles, we reached some threshold value of the dopant in the system, which here is 10% of the mass of dopant in the nanocomposite. And after reaching this threshold, we also see the diminish in the optical responses from the material. And here we are scanning electron microscopy comes in help to answer this question, why is that? So for 0% of dopant in the system, we can see on scanning electron microscopy that the surface of the material has this wavy-like structure, which suggests that we have nice helical bundles formed in its entirety. Then when we go to the 10% of the dopant that we introduce to the system, we still see the wavy-like structure, but it starts to be partially layered by these untwisted organics. And then after reaching 15% of the dopants, in both cases, the wavy-like structure is under some kind of not formed organic compound, probably, of course, the dopants that it pushed out of the forming helices on the outside of the boundary. The next step for our material was to test its universality. That is why we introduced different types of nanoparticles, gold nanoparticles, into the system, starting with 4 nanometer diameter nanospheres, going up with the diameter to 6, 10, and 15 diameter nanospheres, also testing the gold nanorods with the dimensions of 8 to over 20 nanometers. For each of these systems, we were able to see with the electron microscopy formation of the helices with the nanoparticles. For some, we obtained really good optical responses, which was determined by the size of the nanoparticles and the strength of the plasmon that was in the system. And as a last stop, we were able to test the switchability of and durability of this kind of nanocomposite. That is why we, after preparing such a material, we were heating it up to a phase transition temperature, which is in this case 155 Celsius degrees. And as you can see, at 155 Celsius degrees, the CD response, the optical response from the material was vanishing. And then after another cool down, after another freezing, and upon recrystallization of the helices, the CD responses were showing again. That actually shows us that these kind of materials can be switched on and off from its optical properties. To summarize, the freezing-based approach towards chiral plasmonic films is kind of straightforward universal strategy that helps us form these and obtain these chiral films in a bulk scale. We have confirmed that such materials exhibit chiral plasmonic properties if doped with small amounts of chiral additive. And this research enables us fabrication of thin film nanostructures with chiral properties based on a chirality transfer from low molecular weight dopant to a supramolecular structure through length scales. Thank you so much.
So thank you very much for your report. So any questions, please, if somebody have? Okay, so once more, thank you. Okay, so the next reporter is Dr. Mateusz Balasz.
Okay. Hello, everyone. I will share my screen in a second. Okay. So, can you hear me and see my presentation?
Yes, we can hear you clearly and coherently.
Okay. Once again, hello everyone. My name is Matej Balasz. I'm from Institute of Geotechnics in Slovak Academy of Sciences. I say hello to people from our institutions, which are present in person in Lviv. So it is great that we can work under these circumstances also in this way, in hybrid form. So as you can see, my work is common work of more people working at different institutions. In the first part of my talk, I would like to introduce to you the method with which we were working. And in the second part, I will introduce to you the products which we produce. So I'm working in the Department of Mechanochemistry, which is a process usually concerned with chemical and physico-chemical changes of substance of all states of aggregation due to influence of mechanical energy. This is the definition formulated longer time ago. And if I say to people I'm working with mill, so sometimes they think about coffee grinder, which you can see like on this slide. But of course, the machines which we are working with are different and a little bit more complicated. So here you can see the high energy ball mill, which we very often use for our experiments. So if we imagine this mill to be in this kind of schematic structure, so we can change different types, different milling conditions when we want to achieve the optimum outcome. So we can have different mill types. Then we can have different material of milling chamber and milling balls. So on this picture, you can see different ones. For example, we very often use tungsten carbide, but we can also use zirconium oxide, for example. Then we can change milling time from seconds to hours. We can change the milling intensity or speed. We can change number and diameter of balls. And also atmosphere, because sometimes we work with sensitive chemicals. All these parameters together form milling conditions and create milling environment. We can sometimes use also liquids to help us during synthesis. For these special cases, we have special devices. The biomechanochemical synthesis was something that we introduced in 2017. So we can define it as one-step solvent-free methodology of silver nanoparticles preparation by directly milling in solid state the powders of silver nitrate and plants. So this was our pioneer paper where we used oreganum plant as the reducing agent. Then we also applied this methodology for 3 different plants, which are quite common. And then also another one, lavender. And finally, we also used lichens, which were grown in different locations, also in Antarctica, for example, and we compared the speed of the synthesis, how it will go depending on the place of location of these lichens. And in addition, there was another advantage in this case, that the reducing agents of lichens are insoluble in water, which is a contrary situation in comparison with the plants above. With regards to the eggshell waste, so it's one of the most abundant waste coming from food industry in the world. In 2018, I published a review paper where I covered the applications for which it is suitable after the treatment by high energy ball milling. So definitely this method can boost the application potential of this waste material. There are also some works where the composites from both eggshell and plant material and silver nanoparticles are prepared. In our case, we did not try it in mechanochemical way so far, and this was the idea of the present work. With regards to the synthesis of silver nanoparticles using just eggshell by ball milling, there are such reports. For example, this one I am showing you, there were some kind of composites also together with some polymer, but we have also used eggshell membrane, which is the thin membrane under the eggshell, and this of organic character as the reducing agent also. So it can also be used for the production of silver nanoparticles. So for our experiments, we used 3 powders, silver nitrate as a source of silver, then eggshell, and the plant powder of Thymus serpyllum plant, which is called Materina duška in Slovakia, maybe quite similar in Ukraine. We applied the methodology I was explaining, biomechanochemical synthesis. We have used the planetary ball mill and some defined conditions which we knew were working for the previous systems. And then we have used design of experiments which can help us to decrease the potential number of experiments which are actually necessary if we want to get the optimum conditions. So we changed 3 parameters on 3 levels. We have selected the mass of silver nitrate, the ratio between the 2 reducing agents, eggshell and this plant, and the milling time. So in this way, by performing just 9 experiments, we can get potential answer which combination of parameters is the most suitable to get the best results. We have used various characterization methods, and as potential application, silver nanoparticles are known to be good antibacterial agents, so we tested this in collaboration with the university here in Košice by agar well diffusion method. So going to results, at first we analyzed our powders by X-ray diffraction. So here you can see the patterns of the 9 samples. So in the top 3 patterns, we can see still the non-reactive peaks of silver nitrate, which is also connected with the fact that we have used the highest amount of silver nitrate in these 3 experiments. The peaks of silver should be located at around 38 degrees, more or less. So you can see we have it, for example, in sample T7 and T5, we have quite strong reflection coming from silver nanoparticles. So more or less, this was a good result. Also, we observed the peaks corresponding to calcite, which is the main component of eggshell, calcium carbonate in the form of form of calcite, and its main peak is located below 30 degrees. So this one is present in all the samples. After we obtained our samples, we washed them with distilled water in order to remove non-reacted silver nitrate. And in some of our previous research, we found out that actually the stability of these products, of the S-received products, is not so good, and it can undergo backward transformation. So by washing them, we ruled out this phenomenon. And here in the washed XRD, so you can see the peaks of silver nitrate which were present in samples T7 to T9 are not present anymore. So of course it was washed out during this process. However, we found out the formation of new peaks, mainly in the samples where the content of eggshell was quite high. So the most noticeable are the peaks for T9 samples. So for example, the one at 20 degrees and also the one at 34 degrees, quite broad peaks. And we found that this corresponds to silver carbonate. So during the washing process, it seems that the precipitation reaction occurred, and we have also silver carbonate being formed, in addition to silver, which obviously is also there when we see the XRD pattern. Let's say the nicest XRD pattern was obtained for sample T7, where we can see almost only silver peaks and also some small peak of eggshell. But this founding of silver carbonate is also interesting. We analyzed the samples by Rietveld refinement. We found out that the content of silver 0, which means the successful reduction of the silver nitrate, was different among these 9 samples, and the highest content was evidenced in samples T4 and T7. So for now it's difficult to imagine which milling conditions are important, but we will get there. And also the crystallite size, as you can see, we are in the nanometer range. In some cases the nanoparticles were very small, around 5 nanometers. In the cases where the milling time was longer, it's these samples which you can see 3 quite high peaks there, let's say. So the longer milling time led to increase of the crystallite size of silver. And the difference between S-received and washed samples was not very pronounced in this case. We have used the atomic absorption spectrometry to determine the content of silver in the solid samples. So mainly the third and fourth column are important for us. So in the third one we have S-received content. So this is the content of sample of the in the milled samples, and then we have content in the washed samples in the fourth column. And as you can see, sometimes this content has increased, sometimes it has slightly decreased. We have investigated this phenomenon in our previous research, and of course during the washing process, in addition to washing out the non-reacted silver nitrate, we also wash out some water-soluble or plant components, and this can lead to such changes. In the very right side, there is the ratio between the washed and S-received concentration of silver, and the higher the number, it means the more the concentration of silver has increased. So it means better stability of our samples. So the best result in this case was in the case of sample T5, where this ratio was 1.47. But as you can see, the content of silver there was just 15.6%. So based on this comparison, we have selected the last sample, T9, as the best one, because the content of silver was very high there, and also the ratio was above 1, which means quite a good stability. But of course we have silver also in the form of silver carbonate here. So this sample is quite interesting for further research. We have used analysis of variance to determine the contribution of individual parameters for the responses which we selected. So for example, On the picture A, so here we have silver content in the washed samples determined by AAS. So you can see the mass of silver nitrate was found to have the most important influence, which is quite logical. The more silver nitrate we introduce, the higher amount of silver we have in our samples. So this was quite dominant parameter in the 3 or 4 studied outcomes. But in the last one about crystalline size, as I mentioned in the previous slide, you can see that milling time was the most important parameter here. So the longer we mill, the larger the nanoparticles become. So this is something which we get from the statistical point of view. As I told you, we have selected the sample T9 as the best. And as we were working with a composite containing both eggshell and this plant, which we entitled as SER, from Thymus serpyllum, so of course it was necessary to obtain the samples using just one of these 2 parts from the composite. So the red XRD pattern is for the sample where we use only the plant, and the blue one we used only eggshell. And you can see here, in this case, the XRD patterns of all 3 samples were quite similar, I would say, because we have a lot of non-reacted silver nitrate there. However, after washing, you can see that the XRD patterns where we have used just plant, which is the red one, we do not observe any other reflections except the ones corresponding to nanocrystalline silver. Whereas in the case of pure eggshell, which is the blue one, and the composite, which we have used, we observe calcite reflections, the one around 30, and also silver carbonate again. So silver carbonate obviously formed also when we used pure eggshell, which is a logical consequence. With regards to the silver content in these 2 samples, so we can see that it seems to be slightly higher in the composite sample in comparison with eggshell, where of course we had also the plant, which seems to be stronger reducing agent than eggshell. We subjected these 3 samples to the TEM analysis, which was done at the University of Rzeszów. And as you can see, again, the different morphology, the difference in morphology was similar to XRD. So the bottom sample, where only plant was used, we observed silver nanoparticles of defined shape, I would say. On the right side, in the picture F, we can see something like prisms, which is typical for silver. And in the case of these 2 composite samples, the top 2 ones, so the results are quite similar. However, on the first one, so the composite sample seems to be finer. The nanoparticles are smaller. In this case, the nanoparticles correspond to both silver and silver carbonate there. This is the case of both samples. Also, the selected area diffractions, which we have there, needs further analysis, but more or less confirm the presence of silver in the case of just plant, whereas also silver carbonate can be found in the case of composite and the sample with the eggshell. We also used elemental mapping, which helped us to understand what is the distribution of the elements in these samples, in these 3 selected samples. So if we look at these samples, it's clear that again we have quite similar situation in the first 2 cases, whereas different one in the third one. The first 2, more or less, we have calcium carbonate particles, the red ones, big red ones particle correspond to it, because as you can see, what is the distribution of calcium there, and silver for being present either in the form of silver nanoparticles or in the form of silver carbonate, forms small dots on these big particles. So this is the same situation in the 2 samples on the top. However, in the case of silver nanoparticles with the plant, so we observed silver nanoparticles which are dispersed within the matrix of the plant. On the right side there we used nitrogen mapping because we obviously don't have calcium in the plant, or its amount is quite low. So we use nitrogen as to demonstrate the content of the plant matrix where the plant is present there. And the last part of our work was antibacterial activity, which was used by agar diffusion method. So you can see the experimental photographs on the right side there. We have used the bacteria E. coli to investigate our compounds, and the notation of the samples you can also see. In this slide, also the results of the S received and washed samples are compared, and as you can see, the washed samples exhibited activity only in the case when we use either pure eggshell or pure plant. So the composite, unfortunately, neither of the 9 samples which we prepared has shown antibacterial activity in the concentration which we use, because obviously if we increase the concentration, I am sure we will observe antibacterial activity also in this case. Also, we tested the silver nitrate antibacterial activity, which you can see was quite high in this concentration. And we have used gentamicin antibiotic as a positive control, which you can see also in these Petri dishes there. So I am coming to an end now. So as I told you, the results which we have for now are not satisfactory in terms of antibacterial activity, because composites exhibited lower activity than the nanoparticles prepared using individual elements. But this is obviously sometimes in science it happens that you plan something and you end up with a not so good result. However, there are some points on which we can concentrate and our research can move further on. So first of all, we found out that we can have silver carbonate formation in this reaction. We found out what is the morphology, that these nanoparticles are located on the surface of the grains rich in calcium. And we can also control the ratio between silver nanoparticles and the nanoparticles of silver carbonate, which also can be an interesting idea for the future. So with this, I am coming to an end. This project was mainly funded by the Visegrad Fund, where I was working at the University of Rzeszów on this, and then some further projects also contributed. Yes, I am working in the field of mechanochemistry, and I managed to write a monograph on this topic, which is coming out this year. So if anyone is interested in transforming waste into materials by some environmentally friendly method, you are welcome to contact me or look into this monograph. So with that, I am finishing. Thank you very much for your attention, and I am happy to answer your questions. Thank you very much.
Thank you very much. So if somebody have questions. Oh, okay, no questions. Thank you very much once more.
Okay, bye-bye, thank you.
So the next reporter is Professor Alexander Pochichka. So please. So please, some minutes, wait.
Hello. Good afternoon, ladies and gentlemen. So,
Excuse me, so you will be next, okay?
I'm very thankful to organizers for introduction.
Excuse me, so you will be the next reporter. I'm sorry.
Sorry?
Yes, yes, so you will be the next reporter. So please wait, okay?
Оце листать, далі, назад.
Оце листать,
да.
Це назад.
Але тут знизу указка.
Указка знизу.
Ladies and gentlemen, dear colleagues, I have the honor to represent here the Bakul Institute for Superhard Materials of the National Academy of Science of Ukraine. The theme of our report is effect of surface modification of diamond nanopowder particles on the properties of nanocomposite diamond tungsten carbide sintered from them. The object of our study is of nanodispersant diamond powder. We have used the statically synthesized diamond. The aim of this work is to increase the level of physical and mechanical properties of a diamond polycrystalline composite made from diamond nanopowder to expand the possibilities of its application in diamond tools. As you know, the decreasing grain size is the main method to activate sintering in powder metallurgy. But if we sinter the diamond powders, we obtain another result. As the grain size decreases, the density and physico-mechanical characteristic decrease too. In our opinion, there are at least two reasons for this. The first, the difference in direction between external forces acting on the system and internal capillary forces. The second, the interaction of diamond particles with oxygen and oxygen-containing groups on their surfaces. In the case when the above forces are opposite, the compaction degree decreases, but a mean pressure on the porous surfaces increases. According to our calculation, for diamond powders with particles of size 200 nanometer and below, the temperature and pressure in diamond volume during sintering correspond to the diamond thermodynamic stability region. This excludes the diamond graphitization by a direct transformation of diamond to graphite. The graphitization occurs due to the interaction of diamond particles with oxygen and oxygen-containing groups on their surfaces. So, if we want to sinter diamond nanopowders, we need, first of all, to change the functional state of surface of nano-sized diamond powder. Chemical processing of diamond nanopowder of static synthesis was carried out to remove residues of the solvent metal and non-diamond carbon. The treated powder was heated at a temperature of 700 degrees Celsius in a vacuum in an atmosphere of hydrogen and argon. Based on the study of infrared absorption spectra, it was found that the surface of chemically purified diamond nanoparticles contains hydroxyl groups carbonyl groups and CH groups. Annealing in vacuum and argon leads to the removal of hydroxyl and carbonyl groups and a decrease in the number of CH groups. Annealing in hydrogen causes the removal of hydroxyl and carbonyl groups, an increase in the number of CH groups. A study of the interaction of purified diamond nanopowders with tungsten trioxide powder was carried out during heating in vacuum argon in air of the indicated powders without direct contact of the reagents. In the structure of the IRAD spectra of diamond nanoparticles annealed at temperature about 1000 grad Celsius in vacuum and argon, there is a peak of 1220 inverse centimeters, which is responsible for the presence of tungsten carbon bonds formed by interaction of sublimated tungsten oxide with carbon atoms on the surface of diamond nanoparticles. The most intensely maintained bonds are formed during annealing in vacuum at 600 grad Celsius. So, the rate of oxidation of the diamond nanopowder decreases as a result of the chemical modification of the surface of diamond nanoparticles by tungsten, the formation on tungsten carbide bonds. We usually use a toroid high pressure apparatus for high pressure sintering. The working pressure in this apparatus is 8 gigapascal. Samples of the composite were sintered at a pressure of 8 gigapascal at temperature about 1700 grad Celsius and a sintering time of 20 seconds from a mixture diamond nanopowder and tungsten trioxide powder. Annealing in vacuum at a temperature of 600 Celsius, followed by annealing in a hydrogen atmosphere. You can see the result of high pressure sintering of this mixture. The study of the further composition of the samples by X-ray diffractometry revealed the formation of tungsten carbide during sintering and the absence of non-diamond phases of carbon in the composite. Scanning electron microscopy data indicates the formation of tungsten carbide in the space between diamond grain and at the boundaries between them. An obtaining method of nanocomposite diamond tungsten carbide was developed during the realization of the Nano Program project. It consists in high pressure, high temperature sintering of the static synthesized diamond nanopowder, of which additives of nanoparticles obtained by electrospark dispersion of tungsten in ethyl alcohol. The hardness of this composite is 24 gigapascal. The hardness of the composite samples entered from diamond nanopowder using modification of its particles surface by carbon tungsten groups increases to 32 gigapascal. You can see conclusions which I have reported. Thank you very much for attention.
So thank you very much for the report. So any questions, please? Okay, so thank you once more.
Thank you very much.
Thank you. So the next reporter is Professor Alexander Kuhta. It will be online, so.
Hello.
Hello. So we wait your report, please.
Good afternoon. Oh, just a minute. I'm very thankful to organizers for the possibility to present our study at this nice event. I will tell you about luminescent and some electrophysical properties of molybdenum disulfide nanosheets and in its composites with polymer and graphene nanoplatelets. So, the main goal of our work is a study of luminescent and partly electrophysical properties of molybdenum disulfide nanosheets.
So, excuse me, please, could you switch your presentation, please, because we can't see it.
How to switch? I don't know.
At the bottom of the screen, you can see the button demonstrate screen or something like that. Share screen.
Share screen. It's not shared.
Did you find it?
Yes, I shared.
In Zoom, at the bottom of the program, you can see the green button.
Green button, yes. Green button.
Can you click on it and choose the windows with your presentation.
Oh.
Still not.
Still not. Sorry. So.
F5 maybe.
Yeah. F5. Oh, nice.
Yes, thank you very much.
Sorry, please. So, I'm tell you about luminescent and electrophysical properties of molybdenum disulfide nanosheets and their composites with polymer and graphene nanoplatelets. Oh, nice. The main goal of our work is the study of luminescent and partly electrophysical properties of molybdenum disulfide nanosheets and their composites with polymer and graphene nanoplatelets in solution and thin solid films, because despite much available data on this topic, no detailed information on luminescent properties of such nanosheets have been published to date, according to our information. I will tell you shortly what are molybdenum disulfide nanosheets and present you some information about synthesis and several characteristics, and the optical and luminescent properties, as well as some data on conductivity. Single layer molybdenum disulfide nanosheet forms a hexagonal lattice structure on the top and has three sublayer of atoms. Molybdenum atoms is inside, and sulfur atoms between they close between sulfur atoms. So it seems to me sandwich structure, sandwich-like structure. From, you see, this is for nanodots. The blue bands reveals the increase of optical band gap in the blue region, and in the red one. The blue bands reveal the increase of optical band gap with the decrease of thickness of these nanosheets. The absorption spectrum of our nanosheets presented here contains several bands in the UV spectral range, and from 270 up to 360. Practically no absorption has been observed up to 600 nanometers. The luminescence distribution in molybdenum disulfide polymer composite film you can see in this picture using near-field fluorescent microscope. You can see a lot of randomly distributed light spots of different dimensions. Note that no luminescence has been observed in the solid thin films of these nanosheets and their dense solution. It is because of strong concentration quenching. The typical luminescent spectrum can contain two bands in the red spectral range and a white band in the blue region. Depending on the condition, it is possible to obtain preferably red or blue emission. Blue-only emission has been observed for molybdenum oxide disulfide quantum dots. The origin of this spectrum is due to quantum confinement. Photoluminescent spectra of our nanosheets differ from the spectra of typical nanosheets and quantum dots, though it's more similar than so it's more similar to spectrum of quantum dots. But nanodots have dimensions less of 10 nanometers, which is much less than our nanosheets. Spectral bands are wide and have at least two peaks in the blue region. Only very big red luminescent peak was observed in the red region. Not so red, yes. The relative intensity and position of peaks depend on the excitation wavelengths both in solution and thin. This is spectrum for solution, and this is for thin films. They are slightly different, but it can be explained by the fact that in solution, nanosheets are located chaotically, and in thin films, they tend typically to be in parallel to the substrate surface. It can be concluded from this data that luminescence of the obtained nanomaterials combines the properties of nanosheets and nanoparticles. To discover absorption belt more carefully, luminescence excitation spectra were measured. As a rule, luminescent quantum field does not depend on excitation wavelengths, and absorption and excitation spectra coincide. However, the efficiency of absorption and emission in our case, as you see, is very different. Typically, the emission is more efficient in the region with high absorption. It can be seen that excitation spectra depend also on registration wavelengths. In the case of registration at 420 nanometers, the spectrum contains three peaks. That corresponds to the absorption spectrum. However, more clearly, it can be seen here. And for the thin film, the spectra are normalized and easy to compare. And it's not easy. However, the intensity of peaks or in absorption excitation are very different, pointing out the complicated mechanism of energy transformation in this system. It's not clear yet where this energy is disappeared. Time-dependent luminescent measurement are conducted, and luminescence decay at room temperature, both for solution in thin films, can be fitted by three exponential decay function with three characteristic times. The obtained values are higher than these values presented for red emission in literature, and we can't explain the observed decay similarly to red emission because the nature is different. It's possible to assume that it has a quantum confinement nature. A size-dependent decay has been observed for the emission of many quantum dots, and this explanation can be used in our case. It is possible due to the presence of allylamine protective coating on the surface of nanosheets that conserves a lot of single-layer molybdenum disulfide quantum dots. So our spectroscopic and luminescent results indicate that our sample is a mixture of nanosheets of different thickness and sizes, with particular distribution. Moreover, this mixture contains big part of single-layered molybdenum disulfide nanosheets, which are not aggregated, being covered by allylamine molecules. However, additional studies are required to elucidate a mechanism of energy transformation in this system. The observed phenomena in this material can be used for light wavelength tuning of its emission. Molybdenum disulfide is known to be semiconductor material. The obtained composite materials are electrically conductive. You see the data for pure nanosheet films. Film resistance is 1020, 200 ohms. The highest resistance of polymer composite is 27 mega ohms, and the lowest resistance is for the composite of molybdenum disulfide with graphene nanosheets, 50-50%. It is the resistance of this film is 350 ohms. I want to notice that the thickness of the film is slightly different. It may be changed 2 times, maybe more. And this film is attractive, that is higher conductivity, but unfortunately, in this case, we observed luminescence quenching. So, in conclusion, we have obtained molybdenum disulfide nanosheets covered with a neutral surfactant shell. This materials has gray-blue luminescence depending on excitation wavelengths in a wide spectral region and combining properties of nanoparticles and nanosheets. This is because of the presence of a surfactant shell. The obtained properties of this material can be used for light wavelength tuning of its emission. Graphene nanoplatelets results in luminescent quenching. It is typically all thin films are electrically conducting, and the highest conductivity has graphene molybdenum disulfide composite. Thank you very much for your kind attention, and here my contact data.
Okay, thank you very much for your report. So, if somebody has questions, please. Okay, so the next reporter is Natalia Kowalska, PhD student. No. So, if in this case we have a break. So, for break, 5 minutes. So 5 or 10 minutes, please, you have for rest. And after that, we will continue. So thank you.
to presentation hall. And first speaker after coffee break, Filip Bandalevich from University of Warsaw, Faculty of Chemistry, with report Chiral induction and synthesis of gold nanoparticles with chiral morphology after fast transfer using hydrophobic promethogenic ligands. So please.
Thank you very much. Can you say me about the laser?
Laser button on the this one.
Okay, thank you.
Okay.
Okay, I hope you can hear me well. Yes, okay. So good afternoon, or I should say good evening. I'm Filip Bandalevich from University of Warsaw, and today I shall briefly present you some of our recent advancement in the field of chiral nanoparticles, especially morphologically chiral nanoparticles. And in this work, in this presentation, I will start with some of our chiral motivation, and then I will go through the main dish of this presentation, which is the synthesis of those types of nanoparticles, and then further modifications, which are our most important influence in this field. So starting from our motivation, as you can see, as you can see from other presentations from my laboratory, we are highly interested in the chiral nanomaterials, and we are also advancing in the field of synthesizing nanoparticles, from my part especially in aqueous hydrophilic synthesis of those nanoparticles. And from those two ideas we thought about going into the chiral nanoparticle world, especially morphologically chiral nanoparticles. And also the phenomenon of plasmonic chirality, which was discussed by my colleague Dorota. So as we thought about going to this type of chiral nanoparticles, we could go into two ways. And we could go to the improving the chiral nanoparticles that are already in the publications, or go another way to try to synthesize our own new brand chiral nanoparticles. This presentation will be mainly about the first way of improving by the phase transfer method, which will be discussed later. So some main information and some of the methodology that we have used. Nowadays we divide the chiral nanoparticles world into three classes, and the first most important for us is the chiral nanoparticles, morphologically chiral nanoparticles. And those are nanoparticles that have chiral signals because of their specific morphology, geometry, with some kinds of spins on the surface. Second group is the chiral nanoassemblies that you already have heard today. And in that group, we have a single nanoparticle is not chiral, but the whole bulk structure, some supramolecular assembly, is highly chiral. And also the third group, which is the nanoparticles that are chiral because of the chiral ligand on the surface. I will focus on the first group. And in our project, we have used mainly three methods of measurements, two methods of imaging, the scanning electron microscopy and transmission electron microscopy, and also to measure and justify our results. we have used electronic circular dichroism measurements that will show us some chirality measurements. So let's go to the main part, which is the synthesis of the nanoparticles. We have used the most common, most recent ways of synthesizing this type of nanoparticles from the publications like cysteine encoded chirality or amino acid chirality. And in those methods, we use the most common method of synthesizing nanoparticles by the method of seed-mediated growth. And this method is mainly going through steps with growing nanoparticles bigger and bigger. We start with the strong reduction force on gold, strong reduction force like borohydrate, and we achieve 2 nanometer in the diameter spherical seeds. And from those seeds we go further into reduction, and this time we use weaker reducing force, which is ascorbic acid. And at this second step, what we achieve is the 50 nanometer seeds with a specific geometry of, in our case, it was cube octahedron or rhombic dodecahedral shapes, but there are more of those shapes in the chiral world. And the third most important part is the growth of the nanoparticle to the 120 to 50 nanometers in the diameter with the specific geometry terms. And these geometry terms are due to the cysteine or some kind of amino acids or peptides that absorb on the surface of those seeds in the second step. So we have tried to do this synthesis, and as you can see on the results from the scanning electron microscopy on the right side, we have achieved our results, and we have a very interesting geometry of those nanoparticles. Those supposed to be, and they are, the rhombic dodecahedron nanoparticles with the shaped, not shaped, but spinned corners, yes? And those spinned corners are the main reason for the high G-factor signals, as you can see on the left side of the electron circular dichroism. And on these measurements, you can also see the high cotton effect with a beautiful positive signal and a negative signal, and the zero crossing point in the maximum of the absorbance peak. We have also measured the transmission electron microscopy, but as you can see, this is not enough for us. The scanning electron microscopy is more important here because what we mainly want to see is the morphology of those nanoparticles. And from that point, we went to some kinds of the modification, and we wanted to implement those chiral nanoparticles into the other system that should be in a hydrophobic manner. So we had to change the performances of our nanoparticles from hydrophilic to hydrophobic. We have done this by the phase transfer method with covering the nanoparticles with the ligand, with the liquid crystal ligand that was discussed earlier. and mixing with DDT. And after this process, we have achieved the full coverage of our nanoparticles with the ligand. And we have seen that, or maybe I will show this on the other slide, we can see that we have sustained the high chiral signal in different organic solvents like toluene or dichloromethan. And we also have measured some stability in time, and those are really interesting measurements, because as you can see in the DCM solvent, we have a really stable signal over time, and it's measured over 1 hour. And in toluene, we see some movement of the main peaks, and this topic will be this movement might be connected with some kind of coupling or a coupling of plasmons in those materials. And this is the point of our further investigations. So the main result from this project is that we were able to reproduce those type of nanoparticles, and we are able to phase transfer them into the hydrophobic solvents. And in the future, we plan to find some applications that are connected with some optical applications, or maybe some enantiomeric synthesis, so we could synthesize other materials by with the one of enantiomer's advantage by addition of those type of nanoparticles. So that will be it from me. I hope you have some questions.
So thank you for your report, and please questions. No questions, so I ask you, please open a slide with images with different chirality previous. Yeah, that's one. You see your electron microscopy images B and C. Could you comment how you obtain different spin of your chirality?
Yes, of course. Yes, that is a really important part, because in the between the second and the third step, you can add the chiral dopant of one of the enantiomers. Like we have used the cysteine, and you can find the cysteine in the L or S type of L or D type of enantiomers. So if you use L, you usually get the left spin on this free side cross, as I can call it.
Yeah, I see.
Left spin, and if you use the D-cysteine, you get the right spin. Yes.
Okay, thank you. Thank you for answer. Again, our pleasures. And next speaker, Miroslav Sushko from Odessa Mechanical National University, with report effective electrical parameters of systems of fine anisotropic particles. Please.
Thank you very much for this opportunity to present some results. I represent Department of Theoretical Physics and Astronomy, so my report will be dealing with some theory. I heard many reports, but actually little theory, so it like become some introduction to theory about effective electric properties of heterogeneous systems. So electric properties means I am concerned about the effective permittivity, and I will be talking about the permittivity just for the sake of simplicity. But actually the same results will apply to the conductivity, to the complex permittivity, and I will also discuss some generalization of this theory to such systems as composite polymeric electrolytes, solid composite electrolytes, and so on. So you know this theory is very long, has a long story, more than 100 years, when Maxwell started studying the effective properties of systems composed of electric spheres embedded in some media, and so far we have obtained some number of results, but it turns out this is a very difficult subject, because over here I just listed some problems we usually encounter when we deal with these topics. First of all, if you want to try to solve this problem macroscopically from the first principles, you will encounter such problems of calculating many averages, which have to be which can be done using the many particle correlation functions. If you have random heterogeneous systems, this information is usually missing. So usually you can start at the first step, single particle correlation function, or if you talk about system of spheres, you have some pair correlation like Perkusiewicz and so on, but no more. Further approximation, just splitting many particle correlation functions into products of low order correlation function like Perkus, like superposition approach, something like that. On the other hand, we have another approach. This is also medium, effective medium approach. Again, Maxwell Garnett, well known to you, I guess, Brueggemann theory. This is example effective medium approach, but again, usually they are limited to the case when we consider thin particle approximations for the system. Again, we don't control many of these assumptions, approximations, and therefore the result can be checked only by contrasting it with the experiment, which is not good, of course, because actually that's just simple fit. What is the idea of this work? So I would like to present you some new approach, actually, which was developed during recent decade. And this approach I will try to explain briefly by the example of these anisotropic particles, but again, we have many new generalizations, and at the end I will inform you about this generalization. So what is the major idea? The major idea, try to avoid many assumptions and many approximations which we cannot control, and that means we have to give up from considering the system microscopically, but nonetheless we still have to go deeper than just think effective medium theory. So it's like kind of semi-particle theory, and what is very important in this theory? First of all, we avoid many simplifications and many uncontrolled assumptions, but take into account many particle correlations without knowing many particle correlation functions and polarization effect. That's first thing. And the second thing, the kind of harmonization we use. Usually we know when we consider a homogeneous system, we usually assume that one system is embedded into the another, and this other system is usually assumed to be either some real system like a matrix for many composites, or effective medium theory like Brueggemann, and that's it. So again, this is a matter of choice, but not proof. In this theory, we try to show that our approach is consistent only when they use a special kind of harmonization. So actually, we have many particle approach with internally closed harmonization precision, and this is very important. So this is theoretical work. I don't go into many theoretical questions, but I will try to outline the main points of this idea. So let's go further. Look over here. Over here you have examples of system we discussed. So yeah, suppose this is an ellipsoidal particle, or particles of other shape, or this can be core shell particles. And these particles can be core shell, penetrable, semi-penetrable, and so on, hard particles. So we have some results in these directions. So how do we treat the system? Over here, you see the particle. What is denoted here? How do we model our system? We assume we have a real system. Suppose water and particles dropped into this water. So when you have low concentration of the particles, you can say your matrix is water and your your embedded particles are real particles. What about if you have 50 to 50% composition? What is the matrix? You cannot identify. This may be particles and water dropped into the particles. So as the first step, we assume we don't choose the matrix. We just assume that our real system is equivalent. It is electrical dialectical response to some effective system which consists of real components of the system. So particles, matrix embedded into some medium. Some medium is uniform. It described by effective permittivity. Sorry, what happened? Yes. So EF, this is the permittivity of this addition, this fictitious, maybe not, maybe real, fictitious matrix into which all components are embedded, particles and real matrix. So we assume that system can be viewed as a set of so-called compact groups. What do we define by compact groups? This is a large number of particles, macroscopic, so in its properties it's equivalent to a real system. You always can introduce such notion when you consider one-wave response. You can choose the wavelengths very long, so macroscopic regions actually will be look like point light with respect to the electric field. So we assume that we have microscopic particles. We assume that we have particles. View a system as the set of compact group whose sizes is very small. We compare to the wavelengths, but on the other hand, they retain the properties of the entire system. So why this point is very important? The problem is that when you solve the problem about the propagation of electromagnetic field in a homogeneous medium, you solve this problem by using the iterative procedure. You have infinite number of series, but that fact that we consider this approach allows us to state that the main contribution to the effective properties are formed by those effects which can be described, which correspond to the values of integration variables where the internal propagators have singularities. I will explain this. This is theoretical term. So how do we model the system? We assume that our system is just this effective matrix plus deviations from it due to the particles and due to the real matrix. I don't describe this further. Go first. Look here, permittivity. We combine, how do we find? We combine our compact group approach, I will describe it later, with some additional considerations like well-known Hashin-Strickman theorem or the validity of Barré condition and so on. After that, we use the standard procedure of averaging of the electric induction. This is based on so-called ergodic hypothesis. You know, when you have mixture of fine particles, statistical averaging can be replaced by averaging over volume, so they give the same results, and we use this fact. And finally, if you have conductive system, you can also introduce a definition as an effective complex conductivity. Okay, let's go first. Next, how you solve the problem. So you have a heterogeneous system. You have a probing field This pro-Woodin field satisfies certain equation. You solve this equation by the iterative series, and you have very infinite series where you have products of propagators, so-called propagators. This is green function of the respective equation, and products of these deviations due to compact groups. Since these compact groups are very large, spatial correlation between these groups are negligible, and we take advantage of this fact. And finally, we use a special presentations for the propagator. This is mathematical tricks from the theory of generalized function or distributions. And which means what? If you have a real propagator like this, you can represent it as the sum of three propagators in the sense that any integral of this real propagator and its presentation gives the same result. So this is mathematical questions. I don't discuss it, but we use it, this fact. So statistical averaging. Each fact, the system is macroscopically homogeneous, we assume it, and therefore compact groups are statistically homogeneous and isotropic. Long length limit, and finally negligible correlation between groups. As a result, you can single out the contribution of this group, macroscopic group. Actually, the system itself can be macroscopic, compact group. And this is, you see this series, they look very long, they look very strange, but what is interesting for hard particles, for instance, you can find these averages very simply, and this series can be summed up, and you got the result. Look over here. At the top, you see the result of summation of this series for anisotropic particles. These particles can be anisotropic in shape. This particle can be anisotropic in substance properties, and these particles can be inhomogeneous. So the general results over here. Over here you have some parameters. I will describe the meaning of these parameters very simply. Look here. You know the well-known Maxwell-Gardner type of harmonization. Let's take our formula and apply this kind of harmonization. You immediately obtain so-known formula which is called Lorentz equation, where alpha is the effective polarizability. Another example, you have ellipsoids. These ellipsoids are anisotropic in shape, but they also may be anisotropic in their electric properties. When we consider this system, again, we obtain this formula where we have the effective polarizability. And look here, this is this formula when you describe a mixture of ellipsoids, for instance, the electric permeability, of such system, people usually deal with single particle polarizations. What do we show? We show that actually the effective polarizability of the particle in the mixture is not at all equal to single particle polarizability. This is, for instance, you have just effect of the shape, you see very difficult non-linear relationship between single particle and mixture polarizability. Next example, look here. How do we close this harmonization? We still have a known parameter, which is EF. You remember, E effective, this is the permittivity we are looking for, desired. But it depends on this unknown parameter. Again, what can we do? We can do this in two ways. We just require, you can use different ways of harmonization. For instance, you can say, let's find the effective permittivity using the substitutive equation or material equations. But we also can find the effective permittivity by using, for instance, the requirement that the energy stored in homogeneous system be equal to the energy of the harmonized system. And if you require that both ways give the same results, you have no other choice but to assume that effective permittivity and permittivity are equal. So actually, our approach is consistent only if we use the Brueggemann kind of harmonization and no Maxwell-Gardner. in the limiting case of a diluted system, you obtain the Maxwell-Garnot, but this is approximation. That's our conclusion. Next, this is how to calculate this. We have so-called Hershey-Strickman theorem. We can do it. I don't go into the details. I will answer the question. Another way, just require that if you have a real system and you have boundary conditions for this real system and homogenized system, the boundary conditions should be obeyed for this system too. Again, we obtain this result. So over here, you have further applications. Look here, result, epsilon F equals epsilon effective we look for, and this is the equation which describes the permittivity of the system of anisotropic particles. Look here, what is interesting. In the literature, there is no result by Levi-Strauss. They obtain this result using the Maxwell-Garnot approach to a system of anisotropic particles and using statistical averaging, assuming that the particles are independent. Again, if we assume in our theory that the EF equals epsilon 0, epsilon F equals epsilon 0 as which corresponds to the Maxwell-Garnot, we recover this result. But that means what? This result, which is often used to describe, for instance, polymers, is not correct. Over here, you see, you have to use the Broglie-type approximation. This red line shows that actually your permittivity will be higher. Another example of this equation, look at this equation. Polycrystals. What does it mean, polycrystals? These embedded particles fully occupies all the erbium. You have no matrix, actually. That means the concentration C of this particle equals 1, and this term diminishes. So you got this result, you see over here. This result is also known in the literature. This result obtained by, over here you have references. Avalanda, Cherkayev, Lurie, Milton, classic in this field. Again, this is super result means, but you obtain this result as a consequence of this theory. So, what can we see? We can see that we can suppose we can propose one approach which can use different types of harmonization, Broglie time, Maxwell-Garnot time, to recover the existing formulas. Different formulas, obtained from different assumptions by different authors. But within the same approach, you can recover all these results. In fact, some of these formulas are not correct because they are based on Maxwell-Garnot harmonization. Over here, I just summarized some key references. Maybe you got interested in this topic because I look through a lot of literature, and when I see experimental work, when people try to fit the experiments, they actually have no formulas. I just look at some posters. I found 5 posters over here out 20, where people study these questions and don't use any formula. For instance, you have particles, polymer composites, where you have particles embedded in these components. So we have approach to this. Over here, I give the references.
Please, last minute.
Last minute, so that's last. Look here, first report, this is general ideas of this calculation and approach. Second report, this shows that within compact group approach, you can use different ways of harmonization to obtain one or the other results. That's very flexible method. You can model whatever you like. Third report, this is about anisotropic particle, actually the base of this. And you have 2 more reports, the way of choosing the harmonization procedure, based on the Hershey-Strickman theorem and based on the validity of boundary condition. I would like to draw attention to the last report. I heard here many reports about polymers with core shell structure. So right here we have rigorous solution for core shell particles where cores are penetrable. In this way, the core itself can be inhomogeneous. In this way, we managed to describe the concentration dependence of polymer conductivity, I didn't put it here, but in the last references you can find it, so you can use it. Over here we discussed the electrical conductivity of solid electrolytes, classical Liang experiment. And over here you have some ideas how can you use these formulas to extract the information about the structure. For instance, you have a composite, you put their particles, and usually when theoretical describes these equations, they assume the matrix is not changing. But actually, using the core shell particles with penetrable shells, you can solve inverse problem. Given non-monotonic behavior of the electrical conductivity, you can assume what types of physical mechanisms, in which order, at which concentration intervals they occur. So this is very important because we can show that in some experiments, actually the matrix is doped, its conductivity increases, so when you try to explain using fixed parameters of the components, you will be wrong. So we show that in real polymers, the properties of the components change when you add this, when you mix these components, and sometimes you can predict in which way it changes. Thank you very much for your attention.
Thank you for your report. Maybe questions?
Yes.
Thank you for the report. I have very short question. Any restriction to type of particles and matrix? Can be it conductive particles or dielectric or semiconductor?
Dielectric, conductive.
So no restriction for
No,
matrix?
that's actually the same formulas because I choose permittivity because it's simple to explain. Because when you have conductivity particles, you have to work with complex permittivity. You have to do special passing to special limits. And even more, that's an interesting question, by the way. When you have a conductive particle, everything, the result will depend on the frequency that you use. Because it turns out that there is some inequality which when the frequency of the probing radiation is smaller than some value, the property will behave like conductive. If the frequency becomes higher, it will behave like a dielectric. So it's very in static case, these formulas for static conductivity is absolutely the same.
Thank you.
So thank you for report, thank you for questions, and please, next question. Next speaker. This one, Agnieszka Jedrych from University of Warsaw with report a novel method of ordering nanoparticles in photosensitized organic nanotubes.
Okay, which one is your presentation?
PDF version.
Oh, PDF.
Yeah, I hope that it will work.
Okay.
Agnieszka Jedrych, so please.
Okay, I think it will work. So, good afternoon. I am Agnieszka Jędrych and I am a PhD student at the Faculty of Chemistry, University of Warsaw. Today I want to tell you about multi-responsive nanomaterial, which is based on photoswitchable organic template and liquid crystalline plasmonic nanoparticles. So, main topic of my research is this compound, which is presented here. So you can see dimeric molecule with azobenzene group on both sides of it, and the short carbon chain, which connect those two parts. And first time this compound was published in 1995. So authors of this paper presented the way of synthesize this compound and some basic physicochemical results based on polarized optical microscopy measurements. 11 years later, Professor Hideo Takezoe from Japan described a method of obtaining homochiral samples by irradiating them with polarized light. The results of his work you can see here. And one very interesting thing about this compound is its crystallographic structure, because this compound was assumed to be B4 phase or dark conglomerate phase. But Professor Araoka described in his paper that this compound can change the structure in the presence of the solvent. So if we add small portion of the solvent, we can observe two forms presented here. But when we talk about this compound, we need to add a couple words about the photoswitchability. As you can see shorter, and we observe strong increase of the polarity of my template. So at the beginning, I decided, to conglomerate phase pictures, microns, so it allows us to observe the properties of this material in a bulk scale. What's more, let's look at one single tube on those pictures, and we can calculate the diameter, and it's about 139 nanometers. And I should underline that the size distribution is very narrow, only 12%. Lead us to create such model of my tubes, as you can see on the right side. So we can see layers which are curved, and still we have I decided to check how the cooling rate which impact it will have on the quality of my material. So as you can see, if the cooling rate is too big, so the cooling rate is around 20 Celsius degree per minute, we obtain a lot of tubes, but nanoparticles are rather stick outside them, not inside. But on the other hand, when the cooling rate is relatively low, only half Celsius degree per minute, we can see tubes filled with nanoparticles, but those tubes are very short and chaotically ordered. So in my opinion, the best results are obtained for samples cooled with the rate 3 Celsius degree per minute. So optimization process had one more advantage. So on one of the TEM grids, I was able to capture the process of formation of my tubes. So as you can see here, we see layers of my molecules and nanoparticles, and what's more, we can see the wall of the tube. The length is about 53 nanometers. And now we should compare this result with this result. So this is a result obtained thanks to small angle X-ray scattering. And here we can see that we have a strong signal for the periodicity, about 5.3 nanometers. So it is highly probable that the wall of the tube is created by 10 molecules connected to each other. And when we perform some short calculation, we can see 33 nanometers. And in order to deeply examine my hybrid nanomaterials, I decided to compare those two methods, so electron microscopy and X-ray diffraction, one more time. And here you can see the TEM image of my material, and you can observe that nanoparticles are packed inside tubes and still are individual ones. They are not melted together or something like that. And I calculated the distances between nanoparticles in the tube, and this distance is about 9.07 nanometer. And when I performed X-ray diffraction for this material, you can see that I observe very similar signal for periodicities 9.1 nanometer. And what's more, here you can observe how the crystallographic structure of my material is changing with increasing temperature. And here we have first external stimuli which can change my structure of my materials. It's temperature, because above 75 Celsius degree, I lose the ordered structure, and as a consequence, the properties of my material. And second factor which can change the structure of my material is UV radiation. And you can see on the left is a TEM grid with my nanotubes and nanoparticles inside them. And next the same TEM grid I irradiated by UV radiation and put one more time into the microscope. And now you can see that organic molecules create layers, and over it we have monodomains created by nanoparticles. And next step, the same TEM grid was irradiated by visible light, and we can observe tubes, but now most of nanoparticles are outside them. We think that that's the reason of absorption of UV radiation, because we changed the polarity of the matrix and nanoparticles were pushed out. And that's why most of nanoparticles are outside the organic tubes. Next, I checked the chirality of my material, and I used polarized optical microscopy to obtain this goal. We can see that under cross polarizers we didn't see any structures, and when we slightly decross them, we can observe two domains with different colors and different signs. And for this material, I performed a CD spectroscopy, and I observed very interesting signals. And the value of G-factor, dimensionless G-factor, is in order 10 to minus 2 power. So it's very impressive result. And as you can see here, I tried to find the reason why I observed such chiral answer of my material. And in my opinion, it's the reason of this behavior is the structure of one single tube, because we have curved layers, then can be left or right-handed. And that's the reason why I observe such strong signal. And to sum up, I obtain a multi-responsive material. So we have organic nanotubes with nanoparticles inside them. And one additional advantage of my material is the chirality. Thank you so much.
Thank you for report, and please question. Questions? So thank you again. Please, next report, Dr. Karina Valihura from Vladimirovich Pisarjevsky Institute of Physical Chemistry of National Academy of Science of Ukraine, with report catalytic property of manganese and aluminium cerium oxide system in gas fast conversion of ethanol to 1-butanol in flow reactor.
Сейчас, секундочку.
Я ще перед цим не сьогодні, тобто раніше на пошту скидала, чи треба було сьогодні. Okay. Hello everyone, my name is Karina Valigura. I am from Department of Catalytic, Oxidative and Reductive Processes from Pisarjevsky Institute of Physical Chemistry, and I will tell you about one of my recent researches. The creation of process of the production of industrially important substances using renewable raw materials is one of the promising areas of research in the field of organic synthesis. Ethanol obtained from the non-food bio-raw materials could be the basis for the production of a number of valuable compounds, in particular 1-butanol. 1-butanol is mainly used for the production of acrylates, esters, as a solvent, and it also could be perspective fuel, which is more desirable than ethanol. And the industrial method of its production based on petroleum raw materials and has many disadvantages. Therefore, the process of obtaining of this alcohol from bioethanol could be the environmentally friendly alternative. And this process could be realized as via Gerber reaction, which consists of doubling of carbon chain and involves the steps of dehydrogenation of initial alcohol, aldol condensation, dehydration, and the reduction with the formation of the target product. The objects of study are magnesium, aluminum, cerium oxide systems. Their attractiveness in comparison with other known is due to their bifunctional acid-base properties and the tunable characteristics which can be made by changing the ratio of active components during the synthesis. Earlier, we already studied magnesium-aluminum oxide systems with different ratio. The ratio of magnesium to aluminum was found one of the critical parameters influencing their acid-base characteristics and catalytic characteristics. Namely, the most active and selective catalyst toward butanol formation is system with the ratio of 2 and with acid-base capacity ratio near to 3, and it gives the selectivity of butanol near 65%. The introduction of modifying additives such as cerium could be used to regulate the acid-base and catalytic properties of the systems. A series of ceri-containing hydroalkyds was synthesized, and after calcination, only reflexes of magnesia and ceria are present, and the absence of reflexes of alumina is explained by the formation of the amorphous phase. The micrographs of the samples 2 and 3, they demonstrate the plate-like crystals of 150 nanometers in length and 1520 nanometers in width, whereas the sample 1 consists of more amorphous aggregates. And the uniform distribution of cations of aluminum, magnesium, and cerium on the surface of the systems was confirmed via ADX elemental mapping. According to 27 aluminum NMR data, there are 2 pairs of octahedrally and tetrahedrally coordinated aluminum cations. The first pair is attributed to a mixed magnesium-aluminum oxide phase, and the second one two-phase of HAMA aluminum oxide. And in addition, for the sample 2, it was detected the penta-coordinated aluminum cations, which may be due to the formation of aluminum, oxygen, cerium structural fragments. Using the XPS method, it was found that cerium cations in the samples are in states of 4+ and 3+. This may indicate the presence in the studied systems some separate phase of cerium 203 or mixed cerium magnesium, cerium aluminum oxides, which was not detected by X-ray diffraction. Quasi-equilibrium thermal desorption of ammonia and carbon dioxide were used to determine acid and base characteristics. It was found that the introduction of aluminum in cerium cations in magnesia leads to a drastic decrease in acidic and basic characteristics. And the highest concentration of such sites was found for the samples magnesium, aluminum, cerium 2 and 1. Catalytic behavior of oxide systems have been investigated in a flow reactor under atmospheric pressure during 8 hours of work. And it was found that sample magnesium, aluminum, cerium 4, it provides the highest initial butanol yield, 11%, but it very quickly lose activity. This sample characterized by the highest concentration of acidic sites, and it could be the reason of the formation of other side products. The most active, selective, as we see, for the target process is sample magnesium, aluminum, cerium 2. It provides the initial selectivity 68%, and it's more stable in work in time compared to others. Therefore, we compared the most active samples with cerium and without. According to the TPD analysis of ammonia and carbon dioxide, the addition of cerium helps to increase the concentration of acidic and basic sites on the surface. The introduction of cerium cations during the hydroalkyd synthesis leads to increase in selectivity from 65 to 68%. In the optimal ratio of acid and base sites is 3, which near to the close to the sample, unmodified sample, and also the rate of transformation of ethanol, the rate of butanol and acetaldehyde formation are also increases. Also, there is the problem of reduced activity of catalyst in time as a result of deactivation. And the 13 carbon NMR spectra obtained after 12 hours of work of catalyst are shown, and it was detected on the surface the adsorbed ethanol, groups of carbon atoms in different alkyl groups, esters, and acetic acid. The signal of unsaturated aldehydes and ketones are absent, and it also should be noted that for a serum containing sample, there are signals of aromatics, which can be formed by cyclization reaction of unsaturated aldehydes and ketones, which was not detected here. However, the catalytic properties of the studied samples, they are fully regenerated after of 1 hour treatment at 773 kelvins and in airflow. Thus, a detailed study of acid-base characteristics of magnesium aluminum serum hydroxide derived oxides as catalyst for vapor phase condensation of ethanol to 1-butanol in a flow reactor under atmospheric pressure was carried out for the first time. And for effective performance in the target process, the ratio of catalyst oxide components should provide acid-base capacity ratio close to 3, and the highest initial selectivity is reached 68%. Thank you for your attention.
Thank you for your report, and please questions. So if we do not have questions, thank you again. And please, the next Dr. Fatih Dogan Koka from Ersis University with report synthesis of kappa hybrid nanoflower with their antimicrobial activity. So if you do not have speaker, next by the program, Dr. Vitaly Horny from National University of Life and Environmental Science of Ukraine with report synthesis and luminescence properties of phosphate molybdate glasses and glass ceramics doped with europium ions. Please.
Good evening, dear colleagues. I'm Vitaly Cherny from National University of Life and Environmental Sciences of Ukraine. This work was conducted together with scientists from Taras Shevchenko National University of Kyiv and devoted to interesting materials like glass ceramics doped with rare acid ions. What was the motivation of our research? We focused on the materials that can provide nice light yield from under illumination with blue light. This material can be used as covering for light-emitting diodes. You know that light-emitting diodes are very efficient source of illumination. In particular for illumination for in-home. And these light-emitting diodes, most of them are based on so-called phosphor-converting technology. So you have small semiconductor chip that provides blue light. This chip covered by some matrix with oxides or sulfides, and blue light from semiconductor chip transformed into green, red, or yellow light, and we obtain white light as combination from blue light from chip and yellow or green, red light from luminophore, phosphor. Two disadvantages we want to overcome for such system. It's low efficiency of such type of compounds in transforming of blue light into red light. And also when we talk about commercially available white light emission diodes, we should emphasize on the matrix. Matrix that can be silicon of some kind. This matrix possesses illusion of its optical characteristics under action of high light fluxes and also under action of high temperatures. So we need to improve characteristic of light emitting diodes by elaboration of new phosphors and also elaboration of new matrices. And such studies actively performed in the overworld. I'm sorry. Thank you. What requirements for phosphors? These materials should effectively transform blue or maybe ultraviolet light into yellow or red light. Also, these materials should have high quantum yield, good thermal stability, and low toxicity. What about matrices? Also, we need good transparency, optical transparency in the region where phosphors emit light. Also, we need stability of characteristics like the transparency under action of high temperature, high light fluxes, humidity, and so on. And also, low toxicity is very desirable. What about phosphors in matrices? In addition to these requirements, we need to minimize the light scattering on inhomogeneities in the system. This light scattering usually related with mismatch between refraction indices of phosphors and matrices and mismatch between thermal expansion coefficients. We believe that rare as doped phosphate molybdate glass ceramics can be such phosphor in matrix, phosphor in glass that satisfy all these requirements. Synthesis of glasses and glass ceramics was performed by so-called melt quenching. Glass preparation was performed on the base of these raw materials, and with some such composition, glass was obtained. When glass ceramics was synthesized, addition of molybdate compound was used to initial glass, and we obtained small amount of molybdate compound in our initial glass. The concentration of the molybdate compound you see very, very small. Also, we doped glasses with europium ions by adding europium oxide in the quantity of 0.5 and 1 weight%. Methods. We used few methods for sample characterization. It's powder diffraction. It also was infrared absorption spectroscopy, scanning electron microscopy, and also photoluminescence spectroscopy. Results of sample characterization. Thermal gravimetry shows that our samples possess very, very small hydroscopicity. You see only about 1.5% of water in mass presented in our samples. Also, we see that some phosphate compounds can be crystallized in the system when we cool melt to these temperatures. Here are some specific X-ray diffraction patterns that corresponds to our samples. First one is glass. Second one is glass ceramics with highest concentration of molybdate crystals. You see only white, unstructured bonds in the XRD pattern. That means that only amorphous phase is present in both samples, as in glass, also in glass ceramics. Infrared absorption spectroscopy shows that we have phosphates and molybdate groups. They vibration in the absorption spectra. Also, we have combined groups that have linkage between phosphor, oxygen and phosphor oxygen and molybdenum. Scanning electronic microscopy showed us interesting observation. First of all, we use it for synthesis polycrystals with range of grains from 100 nanometers and up to about 2 micrometers. So submicronic and micronic crystals. And on scanning electron microscopy here, 70 micrometers. You can see that we obtain crystallites with about 20 micrometers in size. So first we think that it's growth our molybdite. But chemical element analysis has shown that some of our crystallites melted partially or completely and transformed into compounds that have bismuth, molybdenum, and oxygen. So bismuth orthophosphates, this phase. When we doped glass with europium, we obtained great improvement of luminescence properties. Black curve on this slide represents the luminescence spectra of undoped glass. It has 2 bands that corresponds bismuth and molybdenum in oxygen environments. Here it multiplied on 20. When we doped only with half of % of europium oxide in white, we obtained increasing of luminescence intensity more than on 2 orders. I'm sorry, blue. Additional adding of europium up to 1%, further increase luminescence intensity 4 times. And this luminescence reside in the red spectral region, so we obtain glasses with relatively good red luminescence in our system. Praseodymium doped glass ceramics was performed by adding molybdate, those contained praseodymium. This luminescence spectra was obtained at 2 different valences, blue and violet. You see that excited at blue region, relatively narrow band, located near 600 of the nanometers. This band corresponds to some transition in praseodymium ions. When we changed the excitation valence, we obtain white band that correspond to emission of the glass host. And one more example of the luminescence properties is comparison between praseodymium and europium doped samples. Praseodymium samples is black curve, and europium doped samples is green and red spectrum. We have obtained some difference in spectra that related with location of bands corresponding to transition in these rare earth ions. Also, we obtain some redistribution of intensity when we compare two samples with different content of europium. And you can see that all the band under excitation by blue light located in the red region, so we obtain red emitting phosphor in glass. So as conclusion, we can say that we successfully synthesized and obtained glasses and glass ceramics with intensive red luminescences can be used for light-emitting diodes, and also we can use these glasses for covering of solar cell, because in case of solar cells, we also can transform ultraviolet and blue light into red light in order to improve efficiency of the solar cells. That's all. Thank you for attention.
Thank you for your report, and please questions.
My question is, what is the main advantage of your composite material, glass plus crystal, if compared with its components separately? So you can dope, say, glass by luminescence ions and use it in these applications, or alternatively, you can use doped oxide crystals for wide light coverings. But you develop glass ceramics, and what is the main reason to construct this complex material and not to use separately its components?
Thank you for the question. I start from the last. Why not only crystals? Only crystals hard to use it. In order to cover lead with only crystals, you need to use some matrix that have good adhesion on the semiconductor chip. So you can't just put your crystal on the light-emitting diode that produces blue light, because you just shake such system, all crystals put down. You need some adhesive, like silicon. This silicon, under action of the high temperatures and high light fluxes, it transforms from transparent to yellowish compound. So you lose some light from the light-emitting diodes. And why not on the glasses? You know that glass with rare earth ion have much lower absorption than crystals with same rare earth ions. So we think that combination of glass as host and crystal as active element will greatly improve the possibility to create light-emitting diodes. That's all.
Okay, thank you.
One more questions. I have one question. So, are you compare measurement? Are you do measurements of quantum yield of your compounds and compare with maybe commercial?
Unfortunately, not yet, but this compound, molybdate, these crystals, have high quantum yield. It must be about close to unity. We suppose because similar compounds have very high quantum yield when doped with europium. But we will provide studies on this issue of quantum yield.
Okay, thank you. Thank you for reports, thank you for answers, thank you for questions. And next speaker in our program, Piotr Suskavich from University of Warsaw. Are you present here? So, if no, it was last report. No, online is absent also. So, we finished today's program. Thank you for all participants. Thank you for speakers and organizer committee. So have a nice evening and see you tomorrow.